The telegraph operator in Washington, D.C. had been on duty for 6 hours straight when his equipment tried to kill him. It was the morning of September 2nd, 1859. The sun was already high. The air in the telegraph office was warm, thick with the smell of hot metal and burnt insulation. And then, without any warning, the brass keys on his desk began to spark. Not the gentle flicker of a loose connection, not the routine crackle of a storm somewhere along the line. These were arcs of white-hot electricity, jumping from the equipment, scorching the wooden desk, filling the room with the acrid bite of ozone and burning varnish. The operator lunged backward. The room was lit up like a thunderstorm had moved inside. He was not alone that morning. Across the United States, across Canada, across Britain, France, Germany, Scandinavia, and deep into the Russian Empire, telegraph operators were experiencing the same thing simultaneously, without explanation. Some were burned. Some received electrical shocks powerful enough to knock them off their chairs. At least 2 telegraph stations caught fire. And here is the thing that should stop you cold. The telegraph was the most sophisticated technology on Earth in 1859. It was the internet of its age, the nervous system of modern civilization. Banks depended on it. Railroads depended on it. Governments depended on it. Military commands traveled through it. Stock prices, weather warnings, news of wars and elections. All of it moved through roughly 140,000 miles of copper wire strung across the industrialized world. And in the space of a single morning, that entire system was either paralyzed, destroyed, or, in one of the strangest episodes in the history of technology, operating entirely on its own power, with no batteries connected at all. Telegraph operators in Boston and Portland, Maine, would later report that they disconnected their batteries completely and found that their instruments continued to transmit and receive messages using nothing but the electricity pouring through the air itself. Think about that for a moment. The atmosphere had become a power source. Now imagine that same event happening today, not to telegraph wires, but to every satellite in low Earth orbit, to the global internet backbone, to the GPS systems that guide aircraft, ships, and the navigation apps on your phone, to the power grid that keeps hospitals running, that keeps water treatment plants pumping, that keeps food cold in every grocery store on the planet. This is not a science fiction scenario. This is exactly what scientists at NASA, the European Space Agency, and the National Academy of Sciences have spent years warning about. And the Carrington Event of 1859, named for the British astronomer Richard Carrington, who watched it happen from his private observatory and had no idea what he was witnessing, remains to this day the most powerful solar storm ever recorded in the era of modern technology. The question is not whether something like this can happen again. The scientific consensus is unambiguous. It will happen again. The only question is when, and what the first 12 hours will look like when it does. That is what this video is about. We are going to reconstruct September 1st and 2nd, 1859, hour by hour, as it actually unfolded, from the moment the sun fired a plasma cloud the size of Jupiter directly toward Earth, to the moment telegraph civilization effectively ceased to function. We are going to examine exactly what happened to the planet's magnetic field, to the atmosphere, to the technology of the day, and to the human beings who had absolutely no framework for understanding what was attacking them. And then we are going to look at the science, the real physics of what a coronal mass ejection does to a planet, through the lens of what researchers have reconstructed in the decades since. Because here is the detail that most accounts of the Carrington event leave out. The storm did not arrive all at once. It unfolded in stages. It had phases. And in those phases, there were windows, narrow, terrifying windows, where the course of events could have been different. Understanding those windows is not just a historical exercise. It is a survival manual. So let us go back. Let us go back to the summer of 1859, when the sun was about to do something that would shake the foundations of the most technologically connected civilization the world had ever produced, and when most of humanity had no idea it was coming until it was already there. The story of the Carrington event begins not on Earth, but 93 million miles away. And it begins, as so many catastrophes do, with something that looked, at first, almost beautiful. The world before the storm. To understand why the Carrington event was so devastating, you first have to understand the world it hit. 1859 was not the ancient past. It was not the era of swords and castles and men who had never seen a machine more complex than a water wheel. By the middle of the 19th century, the industrialized world had undergone a transformation so rapid and so total that people who had been born into it were still struggling to comprehend what they were living through. Steam engines were pulling trains across continents at speeds that would have seemed supernatural to anyone born a century earlier. Gas lamps were lighting the streets of London, Paris, New York, and 100 other cities. Photography had been the first transatlantic telegraph cable, a project so audacious that its backers were compared to madmen, had just been completed the previous year, in 1858, though it had already failed by the time the solar storm arrived. Factories were running 24 hours a day. The global economy, in a form recognizable to us today, was beginning to take shape. And at the center of all of it, the technology that tied everything together, the technology that made modern coordination possible, was the electric telegraph. It is difficult, from the vantage point of a world with smartphones and satellite internet, to fully appreciate what the telegraph meant to people in 1859. For all of recorded human history before the telegraph, information had traveled at the speed of a horse. A battle fought in India would not be known in London for weeks. A financial panic in New York would reach London in the time it took a ship to cross the Atlantic. Generals in the field were effectively independent agents. They could not receive updated orders once they had marched beyond the reach of a fast courier. The telegraph changed all of that overnight. Suddenly, information moved at the speed of electricity. A message that once took 3 weeks to cross the Atlantic now arrived in minutes. Stock markets in different cities began to synchronize. Governments could coordinate their responses to crises in real time. For the first time in human history, the world began to feel, not just metaphorically, but practically, like a single connected place. By 1859, the United States alone had roughly 50,000 miles of telegraph wire. Britain had its own extensive domestic network. Continental Europe was connected. The Russian Empire was in the process of constructing lines that would eventually stretch all the way to the Pacific. The dream of a fully wired planet, a planet where any 2 points could communicate instantly, was not just a dream. It was already half built. And all of it, every mile of wire, every relay station, every battery-powered transmitter and brass receiver, depended on one fundamental assumption: that the electrical environment of the Earth was stable, that the currents flowing through those copper wires were only the currents that human beings put there. That assumption was about to be shattered. Now let us talk about the sun. Most of the time, The Sun is a remarkably well-behaved star. It burns steadily, reliably, predictably. The energy it produces has varied by only tiny fractions of a percent over millions of years. Life on Earth evolved in the light of a star that, by cosmic standards, is almost boringly consistent. But the Sun is not a simple furnace. It is a churning, roiling ball of superheated plasma, gas so hot that electrons have been stripped entirely from their atoms, creating an electrically charged fluid that behaves according to the laws of electromagnetism as much as the laws of fluid dynamics. And that plasma is in constant, violent motion. Beneath the surface of the Sun, a region called the convection zone, enormous columns of hot plasma rise toward the surface, cool slightly, and sink back down, creating circulation patterns on a scale that dwarfs anything in our experience. These circulation patterns drag and twist the Sun's magnetic field lines, stretching them, tangling them, building up enormous reservoirs of magnetic energy that, periodically, release themselves in explosive events called solar flares and coronal mass ejections. A solar flare is a burst of electromagnetic radiation, X-rays and extreme ultraviolet light, that travels from the Sun to Earth in roughly 8 minutes, moving at the speed of light. When a powerful flare hits Earth's atmosphere, it ionizes the upper layers on the day side of the planet, disrupting radio communications and interfering with navigation. A major flare is a significant event, but it is, in a sense, only the opening act. The coronal mass ejection, the CME, is the main event. A coronal mass ejection is exactly what it sounds like: a massive eruption of plasma and magnetic field material from the Sun's outer atmosphere, the corona. When the Sun fires a CME, it is not sending a wave of radiation. It is sending matter, billions of tons of charged particles, traveling at speeds that can range from a few hundred kilometers per second to several thousand kilometers per second, wrapped in a magnetic field that can be 100 times stronger than Earth's own. When a CME hits Earth, the effects depend critically on the orientation of its magnetic field. If the CME's magnetic field is pointing in the same direction as Earth's, northward, the two fields deflect each other, and most of the energy glances off. Earth's magnetic field is a shield, and a northward-pointing CME bounces off that shield. But if the CME's magnetic field is pointing southward, opposite to Earth's field, something very different happens. The two fields connect. They merge. In a process called magnetic reconnection, the CME's field essentially tears open Earth's magnetic shield and pours billions of tons of charged particles directly into the planet's magnetosphere. What follows is a geomagnetic storm. And in September of 1859, the Sun fired a CME that was, by every measure scientists have since been able to reconstruct, one of the most powerful in at least the last 500 years, and possibly much longer. But here is the detail that makes the Carrington event truly extraordinary, and that most popular accounts skip over almost entirely. The storm of September 1st and 2nd, 1859, was not the first event of that solar season. In the days and weeks before the Great Storm, the Sun had already been unusually active. Solar astronomers, and in 1859 there were a growing number of dedicated amateur and professional observers with telescopes and the leisure to use them, had been tracking an unusually large and complex group of sunspots on the solar disk. Sunspots, those dark regions on the sun's surface where intense magnetic field activity suppresses the normal convective motion, had been known since the time of Galileo. By the mid-19th century, the relationship between sunspot activity and the roughly 11-year solar cycle was well established. What was happening in late August and early September of 1859 was not subtle. The sunspot group that would later be associated with the Great Flare was enormous, visible to the naked eye, according to multiple observers, when the sun was viewed through appropriate filtration. It was a region of extraordinary magnetic complexity, a tangle of field lines under tremendous stress. And in the days before September 1st, it had already fired. On August 28th, the sun produced a series of significant solar storms. On August 29th and 30th, more flares. The telegraph networks of the time experienced disruptions. The aurora, the northern and southern lights, normally confined to high latitudes near the poles, appeared at unusually low latitudes, visible across much of the United States and Europe. People noticed. They wrote about it in their diaries and their newspaper columns. In many places, the aurora was so bright on the night of August 28th and 29th that people woke up believing it was dawn, only to discover that it was the middle of the night and the sky was on fire with curtains of green, red, and white light. Telegraph operators reported problems, unexpected currents, garbled messages, equipment behaving strangely. Some lines went down entirely. But the system recovered. The disruptions passed. And most people, including the telegraph operators who were already on edge from the strange behavior of their equipment, assumed the worst was over. It was not over. Not even close. What the preceding storms had done, without anyone realizing it at the time, was something that modern space weather scientists understand very well. They had cleared the path. When a CME travels from the Sun to Earth, it moves through the solar wind, the constant stream of charged particles that the Sun perpetually sheds into space. The solar wind is not a vacuum. It has density, and that density creates a kind of resistance that slows CMEs as they travel. Under normal circumstances, even a fast CME takes roughly 1 to 3 days to cross the 93 million miles between the Sun and Earth. But when an earlier, somewhat weaker CME has already traveled that path, it sweeps the solar wind ahead of it, creating a lower density corridor, what modern scientists call a preconditioning effect. A second CME, fired into that corridor, faces less resistance. It travels faster. It arrives earlier than expected. And that is exactly what happened on September 1st, 1859. The CME that Richard Carrington was about to watch leave the Sun at 11:15 in the morning, Greenwich time, the most powerful ejection in the event sequence, was fired into a solar wind that had already been swept partly clear by the preceding storms. Instead of taking the typical 1 to 3 days to arrive, it would reach Earth in just 17 hours and 40 minutes. 17 hours and 40 minutes. That is not a record that has ever been reliably matched in the era of instrumental observation. Normal transit time, 2 to 3 days. The Carrington CME's transit time, less than 18 hours. And nobody on Earth had any idea it was coming. Let us meet the man whose name this event carries. Richard Christopher Carrington was 33 years old in 1859. He was the son of a prosperous brewer in Surrey, England, which meant he had the comfortable fortune that serious amateur science in the Victorian era essentially required. He had studied mathematics at Cambridge, but his true passion was solar astronomy. He had built a private observatory at his estate at Redhill in Surrey, equipped with a refracting telescope and a sophisticated system for projecting the sun's image onto a white screen, a technique that allowed him to observe and draw sunspot activity with extraordinary precision. For 7 years before the events of 1859, Carrington had been conducting one of the most systematic and rigorous programs of solar observation in the world. Day after day, in all but the cloudiest weather, he projected the solar disk onto his screen and carefully mapped the positions, shapes, and movements of every sunspot visible. His records were meticulous, his measurements precise. He was, by any standard, one of the finest solar observers alive. On the morning of September 1st, 1859, Carrington was at his telescope as usual. The sun was projected onto his screen. The complex, enormous sunspot group was clearly visible. He had been tracking it for days. And then, at 11:18 in the morning, he saw something that no human being had ever witnessed and lived to document. 2 brilliant white patches of light erupted suddenly from within the sunspot group. Not the gradual brightening that sometimes accompanied sunspot changes. Not an optical illusion. 2 kidney-shaped beads of intensely white light, brighter than the solar disk itself, flaring outward from the region of maximum sunspot complexity. Carrington watched, stunned. He ran to find a witness, the standard Victorian scientific protocol for confirming an extraordinary observation. By the time he returned, roughly 60 seconds later, the white flares had already begun to fade. They disappeared entirely within about 5 minutes of first appearing. He had witnessed, without knowing it, the most powerful solar flare in recorded history. At almost exactly the same moment, across England, another meticulous solar observer, named Richard Hodgson, was watching the same sunspot group from his own observatory. Hodgson saw the same white flares. His independent observation, published alongside Carrington's account in the monthly notices of the Royal Astronomical Society later that year, confirmed that what Carrington had seen was real, not instrumental artifact, not imagination. Neither man had any framework for understanding what they had just witnessed. The concept of a solar flare did not exist. The concept of a coronal mass ejection would not be theorized for another century. Carrington himself, in his published account, was careful to draw no causal conclusions. He noted, famously, that he had observed the event and that a major geomagnetic disturbance had occurred the following day, but he declined to claim a connection. "One swallow," he wrote, "does not make a summer." It was characteristic scientific caution. It was also, from the vantage point of history, somewhat poignant. Because at the moment Richard Carrington wrote those careful, qualified words, the plasma cloud he had watched leave the sun was already more than halfway to Earth. It would arrive in less than 9 hours. The 17-hour countdown. Let us freeze the clock at 11:18 in the morning, Greenwich Mean Time, on September 1st, 1859. The flare has just fired. The light from it, traveling at roughly 300,000 kilometers per second, will reach Earth in 8 minutes and 20 seconds. The geomagnetic disturbance that Carrington and Hodgson are about to experience in their compasses, the slight trembling of the magnetometer needles that will be recorded at the Kew Observatory just outside London, that is already on its way. Nothing can stop it. Nothing can slow it. The electromagnetic pulse of the flare is crossing 93 million miles at the speed of light, and it will arrive before anyone on Earth has had time to sharpen a pencil and write down what they just saw. But the light is not the weapon. The light, the X-ray burst, the extreme ultraviolet radiation of the flare itself, is the warning shot. It is the muzzle flash. The bullet is still in the barrel. The coronal mass ejection, the billions of tons of magnetized plasma that the flare has blasted out of the sun's corona, is moving fast, extraordinarily fast. Modern reconstructions, using ice core data and nitrate records from the Greenland and Antarctic ice sheets, along with sophisticated magnetohydrodynamic modeling, suggest that the Carrington CME was traveling at somewhere between 2,000 and 3,000 kilometers per second when it left the sun. To put that in some kind of human scale, the fastest object ever built by human hands, the Parker Solar Probe at its closest approach to the sun, reaches speeds of roughly 190 kilometers per second. The Carrington CME was traveling at 10 to 15 times that speed. It was, by any measure, an extraordinary projectile, and it had a clear path to Earth. Now, here is a question that cuts to the heart of this entire event, and it is a question that modern space weather scientists have spent decades trying to answer precisely. What made the Carrington CME so destructive when it arrived? The speed matters, of course. A faster CME carries more kinetic energy. It compresses Earth's magnetosphere more violently. It drives stronger electrical currents in the ionosphere. But speed alone does not determine the severity of a geomagnetic storm. The orientation of the CME's embedded magnetic field, what scientists call the BZ component, the north-south direction of the interplanetary magnetic field, is equally, perhaps even more, important. Think of Earth's magnetic field as a suit of armor. The armor works by deflecting incoming magnetic fields that are oriented in the same direction, northward pointing against northward pointing. The fields push against each other. Energy is transferred away from Earth, reflected back into space. The armor holds. But the Carrington CME was carrying a southward-oriented magnetic field. Strongly, persistently southward. And when a southward-pointing interplanetary magnetic field slams into Earth's northward-pointing magnetosphere, the two fields do not repel each other. They connect. They merge. In a process of magnetic reconnection that modern physicists understand in precise mathematical detail, but that still produces something close to awe when you consider the scale of it, the Sun's magnetic field and Earth's magnetic field become temporarily, catastrophically linked. The armor does not just crack, it opens. Charged particles that are normally deflected around Earth's magnetic shield pour directly into the magnetosphere. They spiral down along magnetic field lines toward the poles. They energize the radiation belts. They induce electrical currents in the ionosphere, the upper layer of the atmosphere, roughly 60 to 1,000 kilometers above the surface, that are orders of magnitude stronger than anything that layer normally carries. And those ionospheric currents do something that, in 1859, nobody had predicted and nobody was prepared for. They induce voltages in long conducting structures on the ground. Telegraph wires, power lines, railroad tracks, pipelines. Any long conductor running roughly parallel to the Earth's surface becomes, during a major geomagnetic storm, a secondary antenna, picking up the fluctuating magnetic field and converting it into electrical current. The longer the conductor, the stronger the induced current. A telegraph wire running 500 miles from one city to another will pick up far more induced voltage than a wire running 50 miles. In 1859, the telegraph networks of North America and Europe were, without anyone intending it, perfectly designed to act as enormous antennas for a geomagnetic storm. Thousands of miles of copper wire, strung across continents, connected to sensitive instruments at both ends, carrying tiny intentional currents that could be disrupted by even modest amounts of induced voltage. The Carrington CME was not going to deliver modest amounts of induced voltage. But we are getting ahead of ourselves. The CME has just left the sun. It is 1859, and the clock is running. Let us follow the 17-hour countdown, as best as modern science allows us to reconstruct it. In the first hour after the flare, the light arrives. At Kew Observatory, the magnetometers, sensitive instruments that continuously measure the direction and strength of Earth's local magnetic field, record a sharp, sudden deflection. This is the magnetic crochet, the immediate response of Earth's ionosphere to the X-ray burst of the flare, which has ionized the sunlit upper atmosphere and briefly altered the electrical currents there. The deflection is small, but unmistakable. The Kew instruments, among the finest in the world, capture it precisely. A few telegraph operators notice that their lines are behaving oddly. Not badly, just strangely. Small currents where there should be none. A slight degradation in signal quality. Nothing that would cause. After the disruptions of the previous days, it seems like more of the same background noise that has been plaguing the network for a week. Nobody connects the magnetometer deflection at Kew to the white flares that Carrington and Hodgson are still writing up their notes on. Nobody, in 1859, has the conceptual framework to make that connection. In the hours after the flare, the CME is crossing the inner solar system at extraordinary speed. It is, in a very real sense, a self-contained magnetic environment, a bubble of solar plasma with its own embedded field, its own internal structure, plowing through the solar wind like a ship through water. The solar wind it encounters has already been partly swept clear by the preceding storms of late August. The preconditioning effect is real. The CME is not fighting its way through a dense medium. It is, in a sense, running downhill. The hours pass. In Washington, D.C., it is still the morning of September 1st. Telegraph operators are at their stations. The lines are busy. The telegraph is always busy. News from across the country, financial dispatches, railroad schedules, personal messages, all of it flowing through those copper veins at the speed of electricity. In London, it is late afternoon. The business of the British Empire is moving through the wires. In Paris, in Berlin, in St. Petersburg, in every connected city on Earth, the telegraph networks are humming. Nobody knows what is coming. Let us take a moment here to appreciate just how profound that ignorance was, and how different it is from our situation today. In the modern world, we have the Advanced Composition Explorer satellite, known as ACE, positioned at the L1 Lagrange point, a gravitational balance point between Earth and the Sun, roughly 1.5 million kilometers. ACE continuously monitors the solar wind, measuring its speed, density, temperature, and magnetic field orientation. When a CME passes ACE, scientists on Earth receive a warning. That warning is not generous. At L1, a CME traveling at the speed of the Carrington Event would provide roughly 15 to 30 minutes of warning before impact. 15 to 30 minutes. We also have the Deep Space Climate Observatory, DSCOVR, which has been at L1 since 2015, providing continuous solar wind monitoring. The stereo spacecraft have provided multi-angle views of the sun and solar wind. Ground-based magnetometer networks around the world give real-time readings of geomagnetic activity. Space weather forecasting centers in the United States, Europe, Japan, and Australia run continuous operations, issuing alerts, watches, and warnings around the clock. And even with all of that infrastructure, the warning time for the most extreme CME events is measured in tens of minutes, not hours or days. In 1859, the warning time was 0. Less than 0, actually, because the conceptual framework for understanding what was happening did not exist. Even if someone had detected the approaching CME, which was impossible with the technology of the day, they would not have known what it was or what it meant. The people of 1859 were, in the most fundamental sense, flying blind. As the afternoon of September 1st advances in Europe and the morning hours unfold across North America, the CME continues its approach. It is worth spending a moment thinking about the sheer physical scale of what is crossing the solar system toward Earth. A major coronal mass ejection can contain anywhere from 100 million to 10 billion tons of solar plasma. The Carrington CME was at the larger end of. It was not a narrow beam. It was a broad front, a magnetic bubble that, by the time it reached the orbit of Earth, spanned a region of space far larger than the planet itself. Earth's diameter is roughly 12,700 kilometers. The CME's magnetic sheath was tens of millions of kilometers across. Earth was not going to be clipped by it. Earth was going to be engulfed by it. And as the CME approached, it was doing something that would dramatically amplify its effects. It was sweeping up the solar wind ahead of it, compressing it into a dense, high-pressure sheath of plasma at its leading edge. This sheath, the shock front of the CME, would be the first thing to hit Earth's magnetosphere, and the shock compression would cause its own burst of geomagnetic activity, separate from and preceding the main event. In modern space weather parlance, this is called the sudden storm commencement, the sharp initial jolt that magnetometers worldwide record simultaneously, as the CME's shock front slams into the magnetosphere and compresses it inward like a fist closing around a ball. The Carrington CME's shock front would hit Earth's magnetosphere in the early hours of September 2nd, Greenwich time. The main body of the CME, the sustained blast of magnetized plasma that would drive the storm to its peak intensity, would follow immediately behind. Meanwhile, on the night of September 1st, something beautiful was happening. The aurora borealis, the northern lights, had already been putting on extraordinary displays for several nights, in response to the preceding, smaller storms of late August. People across North America and Europe had been watching the sky with a mixture of wonder and unease. Auroras at this latitude were unusual. Auroras this bright, this colorful, this dynamic, were something most observers had never seen in their lifetimes. Newspaper reporters were already filing stories. Farmers in Tennessee and Georgia were writing in their diaries about curtains of crimson and green light hanging over the southern horizon. In Cuba and the Bahamas, people were watching auroras that had never been seen at those latitudes in living memory. In the Rocky Mountain territories of the American West, gold prospectors and frontier soldiers were stopping their work to stare at skies that seemed to be on fire. The auroras of August 28th through 31st had been remarkable. What was coming on the night of September 1st into September 2nd would make those displays look like a rehearsal. As the Carrington CME spent its final hours crossing the distance between the Sun and Earth, the pre-storm auroras intensified. The magnetic field of Earth was already disturbed, already responding to the altered solar wind conditions that the preceding CME had created. Magnetometer needles at observatories around the world were swinging more than usual. Telegraph operators were noting more interference on the lines. The system was, in a sense, already stressed, already weakened, already primed. And then, in the final hours of September 1st, the Carrington CME reached the edge of Earth's magnetic environment, the bow shock, where the solar wind first encounters the magnetosphere, and the storm began in earnest. The clock was about to hit zero. There is one more thing worth noting before we move into the impact itself. One detail that carries a particular weight when you sit with it for a moment. Richard Carrington, who had watched the white flares leave the sun that morning, spent the evening of September 1st at his observatory. He was still at his instruments. The magnetometer he kept as part of his observing routine was already showing unusual deflections. He was a careful man, a meticulous recorder, and he noted. He did not know that the thing he had watched leave the sun 11 hours earlier was now pressing against the boundary of Earth's magnetic field. He did not know that by the time he woke up the next morning, the world would look different. He did not know that the event whose opening act he had been privileged to witness, an event that would carry his name for as long as human beings studied the sun, was about to deliver its main act to the entire connected civilization of the 19th century. He went to bed, and 17 hours and 40 minutes after the most powerful solar flare in recorded history, the Carrington CME hit Earth. Impact. It begins with a number. At approximately 4:45 in the morning, Greenwich Mean Time, on September 2nd, 1859, the magnetometers at the Kew Observatory outside London recorded something that the instruments were barely designed to measure. The needle swung. Not the gentle, slow drift that characterized normal diurnal variation, the predictable daily oscillation of Earth's magnetic field as the planet rotated through the solar wind. Not even the sharp but moderate deflection that had accompanied the preceding storms of late August. This was a violent, lurching displacement of the magnetometer needle so extreme that it went off the scale of the recording paper entirely. The Kew Observatory's self-recording magnetograph, one of the most sophisticated instruments of its kind in the world, a machine that used a beam of light reflected off a small mirror attached to the magnetometer needle to trace a continuous line on a slowly moving sheet of photographic paper, produced a record that morning that looks, to modern eyes, like the instrument had a seizure. The trace, normally a gently wandering line, explodes off the page in a series of wild oscillations before vanishing beyond the edge of the recording medium entirely. At the same moment, magnetometers in St. Petersburg were recording the same thing. In Paris, in Greenwich itself, in Toronto, in Bombay, simultaneously across the entire sunlit face of the planet and deep into the night side, the instruments that measured Earth's magnetic field were screaming. The Carrington CME had arrived. To understand what happened in the next 12 hours, you need to understand what a severe geomagnetic storm actually does to a planet, step by step, layer by layer. The first thing the CME's shock front does when it hits the magnetosphere is compress it, violently. Under normal conditions, the boundary of Earth's magnetosphere on the sunward side, the magnetopause, sits at roughly 65,000 kilometers from Earth's surface. That is the frontier where Earth's magnetic field is strong enough to deflect the solar wind. The CME's shock front, carrying a dynamic pressure orders of magnitude higher than the normal solar wind, slams into that boundary and pushes it inward. During the Carrington event, modern reconstruction suggests the magnetopause was compressed to somewhere between 25,000 and 30,000 kilometers from Earth's surface, pushed more than halfway to the planet from its normal position. This compression does several things simultaneously. First, it sends a wave of disturbance racing through the magnetosphere, a sudden impulse that propagates at near-light speeds through the magnetic field, reaching every part of the magnetosphere almost instantaneously. This is the sudden storm commencement that magnetometers worldwide record as a sharp, simultaneous spike. It is the handshake between the CME and the planet, the moment the two magnetic environments make contact. Second, it energizes the particles trapped in Earth's radiation belts, the Van Allen belts, though they would not be named or discovered for another. These belts, donut-shaped regions of magnetically trapped charged particles circling Earth, respond to the compression by accelerating their particles to higher energies, producing secondary effects that ripple through the magnetosphere for hours and days after the initial impact. Third, and this is the mechanism that produced the devastation on the ground, the compression and the subsequent magnetic reconnection on the night side of the magnetosphere drives intense electrical currents through the ionosphere. These are the auroral electrojet currents. They flow in massive sheets, hundreds of kilometers wide and thousands of kilometers long, in the ionosphere at altitudes of roughly 100 kilometers above the surface. Under normal conditions, they are a natural feature of the high-latitude ionosphere, concentrated near the poles, relatively modest in their intensity. During a severe geomagnetic storm, they expand dramatically toward lower latitudes, and their intensity increases by factors of 10, 50, 100, or more. During the Carrington event, by every measure available, the auroral electrojet currents were at an intensity that modern scientists classify as off the scale of normal experience. And those currents, those vast sheets of electricity flowing through the sky, were the mechanism that reached down and touched the surface of the Earth. Here is the physics, stated as simply as it can be. A changing magnetic field induces an electrical current in any conductor within its reach. This is Faraday's law of electromagnetic induction, established by Michael Faraday in 1831, just 28 years before the Carrington event. The stronger and faster the change in the magnetic field, the stronger the induced current. During the Carrington event, the magnetic field at Earth's surface was not just changing, it was The rate of change, measured in nanoteslas per minute at ground level, reached values that modern space weather scientists classify as extraordinarily extreme. In some locations, the horizontal component of the magnetic field changed by hundreds of nanoteslas in a single minute. Every long conductor on the surface of the Earth was sitting inside a magnetic field that was doing this. The telegraph wires, thousands of miles of copper strung across continents, were threaded through this convulsing field like needles through fabric. And according to Faraday's law, which does not care about the year or the technology or the intentions of the engineers who built those wires, they became generators. Not small generators. The induced voltages in some telegraph lines during the Carrington event were, by the best modern estimates, in the range of hundreds of volts over the length of a long line. Some estimates go higher. The normal operating voltages of Victorian telegraph systems were in the range of a few volts to a few tens of volts at most. The induced currents were not just a nuisance. They were overwhelming the system by a factor of 10, 20, 50 times the designed operating range. Let us go to the telegraph offices now. Let us see what this looked like from the inside. The accounts that survive from September 2, 1859 are among the most extraordinary documents in the history of technology. They come from telegraph operators writing in their logbooks, from newspaper reporters interviewing operators afterward, from formal reports submitted to telegraph company management, and from a remarkable series of exchanges published in the Journal of the American Telegraph magazine in the months following the event. What emerges from these accounts is a picture of cascading technological failure that unfolded over the course of hours, but also, in some cases, of technology behaving in ways so bizarre that the operators witnessing it had no language to describe what they were seeing. In Boston, a telegraph operator attempting to send a routine dispatch at around 6 a.m. local time found his instrument producing sparks. Not the small, controlled sparks of normal operation. Violent arcs of electricity that jumped from the brass key to nearby metal surfaces, scorching the wooden desk, filling the small office with the smell of ozone and burnt wood. He stepped back from the instrument. He tried to disconnect the line from the battery. The sparks continued. The line was generating its own current, independent of any battery in the building. In Pittsburgh, a telegraph operator received a shock strong enough to throw him from his chair. He was not seriously injured, but the account he gave afterward, published in the Pittsburgh Gazette, described the experience as being hit by a charge far stronger than anything he had encountered in years of working with electrical equipment. In Washington, D.C., the main telegraph office serving government communications experienced simultaneous failure on multiple lines. Operators attempting to clear the lines and restore service found that the anomalous currents would not stop. They were not dealing with a fault in the circuit or a problem with the batteries. They were dealing with a source of electricity that was not in the room with them, not in the building, not anywhere they could reach or fix. In New Orleans, a telegraph operator reported that his instrument was producing a continuous stream of random characters, dots and dashes with no meaning, no message, no pattern, driven entirely by the induced currents in the line. Imagine sitting at a telegraph receiver and watching the instrument pour out gibberish endlessly, knowing that nobody is sending it, not knowing what force is driving it. And then there was the incident that has become the most famous anecdote of the entire Carrington event. The exact exchange has been reported in several slightly varying forms, but the core of it is documented in contemporary sources. Somewhere in New England, the most commonly cited location is the line between Boston and Portland, Maine. Two telegraph operators disconnected their batteries entirely, leaving their instruments connected only to the telegraph wire itself, with no intentional power source in the circuit at all. And they found that they could still communicate. The induced current from the geomagnetic storm was, by itself, sufficient to power the telegraph instruments. The atmosphere was generating enough electrical current in the wires to transmit and receive messages. One operator, in a dispatch published shortly afterward, described working by the auroral current alone for a period of approximately 2 hours. He reported that the quality of communication was sometimes better, sometimes worse, as the storm fluctuated. The current would surge and fade as the geomagnetic activity intensified and relaxed, but that for extended periods the system worked. Think about what this means. The technology that was supposed to control the flow of information, the battery, the key, the human operator making deliberate choices about what to send, had been completely bypassed. The sky had taken over the telegraph network. It was not running on human intention anymore. It was running on the sun. While the telegraph operators of North America and Europe were dealing with the chaos on their lines, something else was happening overhead that was visible to anyone who stepped outside and looked up. The aurora of September 1st into September 2nd, 1859, was unlike anything that had been observed in living memory, and for most of the observers who witnessed it, unlike anything they would ever see again. The aurora australis, the southern lights, was seen as far north as Queensland, Australia, and Chile. Normally visible only from Antarctica and the extreme southern tip of South America, it appeared over populated regions that had almost no tradition of aurora observation. Accounts from Australia describe workers on sheep stations stopping in the middle of the night, believing the distant town or a neighboring property was on fire, only to realize the light was coming from the sky itself. In the northern hemisphere, the aurora borealis was, by every account, extraordinary. In the northeastern United States, it was bright enough to read by. Multiple observers tested this specifically. They held newspapers or books up under the open sky at midnight, hours after the sun had set, and reported that they could read the text without difficulty. The light was not quite the steady white of moonlight. It was pulsating, shifting, colored, predominantly crimson and green, with flashes of yellow and white. But it was bright enough to make ordinary tasks possible outdoors. In New England, in New York, in Pennsylvania and Ohio, people were woken up by the light coming through their windows, convinced it was dawn. When they looked at their clocks and found it was 1 or 2 in the morning, and then went outside and saw the sky, many of them recorded a visceral experience of wrongness, of the natural order being violated. The sky was not supposed to look like this. In Cuba, in Mexico, in the Bahamas, latitudes where the aurora is essentially never seen, people were watching the northern sky ripple with curtains of red and green light. In Hawaii, auroras were visible. In Colombia, near the equator, observers reported a reddish glow on the northern horizon. In Rome, the aurora was so bright and so crimson that the city's fire brigade turned out, believing the distant hills were ablaze. In the Rocky Mountain territories of the American West, gold miners at high altitude described auroras so intense that the mountain peaks were illuminated as brightly as by a full moon, in colors that none of them had words to describe adequately. Their accounts, collected in frontier newspapers weeks and months later, read like descriptions of a supernatural event, because in their experience, that is exactly what it was. The Japanese records, the Meiji period astronomical observations and provincial reports, describe aurora sightings across the Japanese home islands, again at latitudes where such phenomena were essentially unheard of in historical memory. The aurora of the Carrington Event was visible from the equator. Let that sink in. But the aurora was not just a light show. It was a symptom. It was the visible manifestation of the same energetic particle precipitation and ionospheric current systems that were destroying telegraph networks across the planet. The light was beautiful. The mechanism producing it was catastrophic for technology. And as the storm intensified through the morning hours of September 2nd, not peaking immediately upon impact, but building, as CME-driven storms do, as the sustained southward magnetic field continued to drive magnetic reconnection and pump energy into the magnetosphere, the failures mounted. In Britain, The main telegraph trunk lines between London and the major provincial cities were experiencing simultaneous. The Electric Telegraph Company, the largest telegraph operator in Britain, was attempting to maintain service on its most critical routes, the lines connecting London to Edinburgh, to Manchester, to Birmingham, and finding it increasingly impossible. Operators were being pulled from their stations when equipment sparked. Relay stations were losing power as the anomalous currents overwhelmed their equipment. In France, the telegraph network connecting Paris to the major provincial centers was experiencing similar failures. The French government's dedicated telegraph lines, the network that carried official dispatches between the capital and the prefectures, went down at various points during the morning hours. In continental Europe, the story was similar. The Prussian telegraph system, the Austrian system, the Russian lines, all reported severe disruptions. In some cases, lines that had been functioning at midnight on September 1st were simply dead by dawn on September 2nd and would remain dead for hours. The disruptions were not uniform in time or geography. The storm was not a single, steady state. It was dynamic, fluctuating, with periods of intense activity and brief intervals of relative calm, as the magnetic reconnection at the magnetopause pulsed and shifted. Some lines that went down came back up for a few minutes, then went down again. Some operators reported being able to transmit during brief, quiet intervals, then losing the line completely when the storm surged. It was, in the language of modern disaster management, a complex, cascading, non-linear failure. And in 1859, nobody had a protocol for it. Nobody had a backup system. Nobody had an alternative communication infrastructure to fall back on. When the telegraph went down, communication went down. There is a dimension of the Carrington event that tends to get less attention than the telegraph disruptions, perhaps because it is less dramatic in the immediate term, but that is, in some ways, more scientifically significant. The storm's effects were not limited to the surface of the Earth. At an altitude of roughly 100 to 1,000 kilometers, the ionosphere, normally a relatively stable layer of ionized gas that serves as a reflector for certain radio frequencies and a conductor for others, was being violently disrupted. The particle precipitation driving the auroras was also dramatically altering the ionosphere's electrical properties. The auroral electrojet currents were flowing through it at extraordinary intensities. What this meant, in practical terms in 1859, was that any technology dependent on the ionosphere would have been affected. Fortunately for the people of 1859, they had no such technology. Radio would not be invented for another 4 decades. Ionospheric communication, GPS, satellite navigation, none of it existed. But the geomagnetic storm also had direct physical effects at ground level that went beyond the telegraph. Compass needles, used for navigation at sea and in surveying, were swinging wildly and unreliably for hours. Ships at sea that were relying on magnetic compasses for navigation in overcast conditions, unable to use stars or sun, were effectively sailing blind during the worst hours of the storm. The effect on compass navigation is documented in multiple maritime logs from September 1859. Ships reported compass anomalies lasting for hours, with needles that would not settle and gave readings that experienced navigators knew were. In 1859, before the era of powered ships made schedules more predictable, before radio allowed ships to communicate with shore, a compass failure at sea in bad weather was not a minor inconvenience. It was a genuine navigational emergency. By mid-morning on September 2nd, Greenwich time, roughly 6 to 7 hours after the initial impact, the Carrington Event had effectively paralyzed the telegraph networks of North America and Europe. Not every line was down simultaneously. The storm was too dynamic and geographically uneven for that. But the overall picture was one of a communication system that had been reduced, in a matter of hours, from the nervous system of industrial civilization to something barely functional, a degraded, unreliable, dangerous network of wires that was as likely to shock its operators as to deliver a message. The companies that owned these networks were losing money by the hour. The governments that depended on them for official communications were effectively cut off from their provincial administrations. The railroads that used Telegraph for scheduling and safety coordination were operating without the communication infrastructure they had come to depend on for avoiding collisions and managing traffic on their single-track main lines. And the storm was not done. The first 6 to 7 hours after impact had been the sudden commencement phase, the initial slam of the CME's shock front, the compression of the magnetosphere, the first surge of auroral electrojet currents. Now, as the main body of the CME engulfed the magnetosphere, sustained, powerful, carrying that persistent southward magnetic field that kept driving reconnection and pumping energy into the system, the storm was entering its main phase. The main phase of a geomagnetic storm is typically the most intense and the most sustained. It is the period when the ring current, a donut-shaped current of energetic ions that circles Earth in the inner magnetosphere, is driven to its peak intensity by the steady injection of particles from the reconnection sites. As the ring current intensifies, it produces its own magnetic field, directed opposite to Earth's main field, which further distorts and weakens the overall geomagnetic environment. The DST index, the measurement that modern scientists use to quantify geomagnetic storm intensity, measuring the depression of the horizontal component of Earth's magnetic field at equatorial observatories, is calibrated so that the most severe storms in the modern record reach values of -200 to -300 nanoteslas. The Carrington Event, by the best modern reconstructions from historical magnetometer records and ice core data, produced a DST value somewhere between -800 and -1,700 nanoteslas. That is not a 2 or 3 times larger storm than the worst modern events. That is a 4 to 8 times larger storm, on a scale that does not exist in modern instrumental records. It was, and remains, in a category of its own. And this is the moment, the peak of the storm, somewhere in the late morning to early afternoon hours of September 2nd, 1859, where we need to stop and ask the question that gives this entire video its urgency. What if this happened today? Not to telegraph wires, not to compass needles on wooden sailing ships, to satellites, to power grids, to the internet, to GPS, to every piece of electronic infrastructure that the modern world depends on to function. The answer to that question, worked out in detail by engineers, physicists, and emergency planners at institutions including the National Academy of Sciences, NASA, the European Space Agency, and Lloyd's of London, is one of the most sobering documents in the literature of civilizational risk. We will get there. We will walk through exactly what the modern models predict, hour by hour, in a Carrington-scale event striking today's infrastructure. But first, we need to finish reconstructing what happened in 1859. Because the story of the Carrington Event is not just about the first 6 hours, or the first 12 hours. It is about what happened in the days and weeks afterward, and what the world learned and failed to learn from the experience. The Hours of Chaos. It is now roughly 7 in the morning on September 2nd, 1859, in the eastern United States. The sun has been up for about an hour on the Atlantic seaboard. The morning shift of telegraph operators has arrived at their stations, or tried to arrive, only to find their night shift colleagues still at their posts, unable to leave, unable to hand over functional equipment, struggling with instruments that were sparking, shocking, transmitting gibberish, or simply dead. In the cities, Boston, New York, Philadelphia, Washington, Baltimore, the telegraph offices that served as the nervous centers of commercial and governmental communication were in various states of crisis. Some had already suffered fire damage. Some had operators nursing burned hands and singed eyebrows. Some had simply shut down, their operators having made the pragmatic decision that continuing to work with equipment that was actively trying to electrocute them was not a reasonable professional obligation. And the public had no idea what was happening. This is a dimension of the Carrington event that rarely gets the attention it deserves. We tend to focus on the technology, the sparking telegraphs, the disrupted lines, the operators receiving shocks. But behind the technology were human beings who depended on that technology for information. And in the absence of information, what filled the void was something that has been a constant companion of disasters throughout human history: rumor, fear, confusion. Let us reconstruct the human experience of September 2nd, 1859, as carefully as the historical record allows. In the major American cities, the first thing most people encountered was not a sparking telegraph or a disrupted communication line. It was the sky. Those who had been awake through the night, and there were many because the auroras of the preceding nights had already established a pattern of people staying up to watch the display, had witnessed something extraordinary. The aurora of the night of September 1st into September 2nd was not just brighter and more widespread than the displays of the previous week. It was different in character. The accounts that survive describe not just curtains and rays of light, but a dynamic, pulsating, almost structured display that seemed to move with purpose. Great arcs sweeping across the sky, coronas, circular arrangements of rays converging toward a single overhead point that multiple observers described as looking like the sky itself was opening. Rapid flickering and pulsation as the aurora danced on timescales of seconds, responding to the fluctuating geomagnetic field below. The colors were extraordinary. The dominant color of a powerful aurora at mid-latitudes is typically red, the signature of energized oxygen atoms at high altitude, emitting light at the wavelength of 630 nanometers. During the Carrington event, the red aurora was over. Multiple observers in the American South described the sky as appearing literally on fire, not metaphorically, but with the physical appearance of flames. Brilliant crimson curtains hanging in the sky, flickering, shifting, appearing in the south, west, east, north, everywhere simultaneously. In the American South, in Georgia, Alabama, Mississippi, states that had no cultural tradition of aurora observation because the northern lights simply did not reach that far under normal circumstances, the response was, in many documented cases, one of genuine terror. Newspaper accounts from the weeks following the event preserve some of these reactions. Enslaved people on plantations across the Deep South who had no way of knowing what the lights were and no access to scientific explanation interpreted them in the frameworks available to them: religious, spiritual, prophetic. Many believed the end of the world was beginning. Some accounts describe large gatherings of people praying through the night, certain that the red sky was the fulfillment of biblical prophecy about the last days. But it was not only enslaved people or the uneducated who were frightened. Middle-class families in Virginia, Tennessee, and the Carolinas were writing in their diaries about fear and confusion. Ministers were receiving parishioners at their doors in the middle of the night, people who had come seeking spiritual reassurance about what they were seeing. Local newspapers, in their editions of September 2nd and 3rd, would carry accounts that mixed scientific curiosity with barely concealed anxiety. In the cities of the Northeast, where the educated population had somewhat more exposure to scientific discourse and where the aurora was a more familiar, if still unusual, phenomenon, the response was more mixed. Many people found the display spectacular and beautiful. College professors dragged their families outside to watch. Amateur astronomers were furiously making. Artists were sketching. But even in Boston and New York, there were people who were frightened. The scale and the intensity of the aurora, its presence in the south as well as the north, its extraordinary brightness, its crimson color, pushed it beyond the range of normal experience for everyone. And then dawn came. And with dawn came the news of what had happened to the telegraphs. The telegraph companies of 1859 did not have public relations departments. They did not have crisis communication protocols. When their networks failed, they did not issue press releases or hold briefings. What happened instead was what always happens in the absence of official communication. The information leaked out through the people who actually experienced it. Telegraph operators talked to each other, to journalists, to anyone who would listen. The stories spread through the coffee houses and newspaper offices and merchant houses of the major cities with the speed that gossip has always traveled, which is to say, very fast. By mid-morning on September 2nd, the commercial districts of New York, Boston, and Philadelphia were alive with conflicting accounts. The telegraph was down. No, it was working, but unreliable. No, it was working fine on some lines and completely dead on others. The equipment was on fire. Operators had been injured. Messages sent the previous evening had never arrived. For the merchants and bankers and businessmen who depended on telegraph communication for their daily operations, this was not an abstract inconvenience. It was a direct financial threat. In 1859, the American economy was already under stress. The Panic of 1857, a severe financial crisis that had begun with the failure of the Ohio Life Insurance and Trust Company, had sent shock waves through the economy that were still being felt 2 years later. Banks were cautious. Credit was. Business confidence was fragile. And now, on top of existing economic anxiety, the primary communication infrastructure of the commercial world had been knocked out by something that nobody could fully explain. The stock exchanges of New York and other major cities did not close. The Carrington Event, unlike a modern grid failure, did not cut off power to the buildings themselves. Gas lamps still worked. People could still walk and talk and trade. But the flow of financial information that the telegraph provided, the price quotes, the market news, the commercial intelligence that allowed traders to make informed decisions, was severely disrupted. Some trades that should have been executed based on telegraph messages received before the storm simply never went through, because the confirming reply never arrived. Some merchants who had sent orders to suppliers in other cities had no way of knowing whether those orders had been received, because the lines were down when acknowledgement should have come back. The financial disruption of the Carrington Event in 1859 was real. It was not catastrophic in the way that a modern grid failure would be, because the economy of 1859 was not wired the way the modern economy is wired. But it was significant. And it was a preview of something that the economists and engineers of the day mostly failed to appreciate in its full implications. Meanwhile, in the telegraph offices themselves, something remarkable was happening. As the storm's main phase continued through the morning hours, the geomagnetic activity remaining at extraordinary intensity, the auroral electrojet currents continuing to flow at levels that dwarfed anything in prior experience, the operators who had not been driven from their stations by sparking equipment were confronting a technical puzzle unlike anything in the literature of their profession. Because the induced currents were not constant, they fluctuated. They surged and faded as the geomagnetic field convulsed. And in the intervals between the worst surges, the currents in the lines would settle to a level that was strong enough to power the instruments, but not so overwhelming as to destroy them. Some operators, driven by a combination of professional duty and sheer curiosity, began experimenting. The exchange between the Boston and Portland operators, working by auroral current alone with their batteries disconnected, is the most famous example. But it was not unique. In several locations across the network, operators discovered that they could transmit during the quieter intervals of the storm by timing their messages to the fluctuations in the induced current, essentially learning to read and use the electromagnetic weather of the moment. This was not planned. It was not the result of any theoretical understanding of what was happening. It was pure empirical improvisation. Experienced telegraph operators using their intimate knowledge of how current behaved in their instruments to adapt, on the fly, to an entirely novel situation. It is, when you think about it, one of the more impressive examples of human technical adaptability under pressure in the 19th century. These men had never been trained for this. Nobody had ever imagined this situation, and some of them found a way to make it work. Not well, not reliably, not for long, but they found a way. The messages that were successfully transmitted during the Carrington Event by auroral current are among the most unusual documents in telegraph history. They were sent sporadically, often fragmentary, sometimes garbled by sudden surges in the storm current. But they got through, at least some of them. Let us now move beyond the telegraph offices and look at other dimensions of the event that were unfolding simultaneously. The disruption of compass navigation at sea, which we touched on in the previous chapter, was more significant than it might initially appear. September of 1859 was not a quiet month in global shipping. The mid-19th century was the golden age of commercial sail, the era of clipper ships, of packet lines running regular routes across the Atlantic and Pacific, of a global maritime trade network that carried cotton, grain, spices, manufactured goods, and hundreds of thousands of passengers between the ports of the world. In September of 1859, the North Atlantic was busy with ships making the crossing in both directions. The route from Liverpool and Southampton to New York and Boston was one of the most heavily trafficked maritime lanes in the world. And in the age before radio, before GPS, before any electronic navigation aid whatsoever, those ships depended on two things for navigation in overcast conditions: the chronometer for longitude and the magnetic compass for direction. The chronometer was unaffected by the Carrington Event, but the compass was another matter entirely. During the peak hours of the storm, magnetic compasses at sea were giving readings that experienced navigators knew were unreliable. The horizontal component of Earth's magnetic field, the component that points toward magnetic north and drives the compass needle, was oscillating wildly. A compass that normally held steady to within a degree or two was swinging by 5, 10, 20 degrees or more, then swinging back, then swinging again. For a ship in open ocean, with clear skies and star sights available, this was a manageable problem. You simply checked the compass against celestial navigation and corrected for the anomaly. But for a ship in overcast conditions, in fog, near a rocky coastline, or in any situation where celestial navigation was not immediately available, a compass that could not be trusted was a genuine danger. The maritime records from September 1859 are incomplete. Many ships' logs from that era have not survived, and those that have often do not mention geomagnetic anomalies in terms that historians can easily identify. But the pattern of compass disruption is well documented from shore-based observations, and the inference that ships at sea experienced the same disruption is straightforward. Whether any ships were lost specifically because of compass anomalies during the Carrington event is not definitively established in the historical record, but the risk was real, and the conditions that created it were real. There is another dimension of the Carrington event that requires attention here, because it is one of the most scientifically significant aspects of the whole episode, and one that connects directly to the question of modern vulnerability. The storm affected not just the surface of the Earth, but the atmosphere itself, specifically the upper atmosphere, at altitudes where the physical chemistry of the air was being directly altered by the particle precipitation driving the aurora. When energetic particles from the magnetosphere rain down into the upper atmosphere, as they do intensely during a major geomagnetic storm, they trigger a cascade of chemical reactions. Among the most significant of these is the production of nitrogen oxides, chemical species that, in the stratosphere, catalyze the destruction of ozone. Modern scientists studying the Carrington event have used ice core records from Greenland and Antarctica to measure the nitrate deposition from the storm, the chemical fingerprint left in the ice by the nitrogen oxide production of the event. The nitrate spike in Greenland ice cores corresponding to 1859 is among the largest in the last 500 years. What this means in practical terms is that the Carrington event produced significant ozone depletion in the polar stratosphere. The scale of this depletion and its duration are still subjects of active scientific research. Work by researchers at institutions including the University of Oulu in Finland, the Max Planck Institute for Solar System Research in Germany, and NASA's Goddard Space Flight Center has refined the estimates considerably in the years since the ice core data first became available. The immediate health effects of this ozone depletion in 1859 were almost certainly negligible. The depletion was concentrated at high latitudes. It recovered over a period of weeks to months, and the population of the polar regions in 1859 was small. But the principle that a sufficiently powerful solar storm can measurably alter the chemistry of Earth's atmosphere is established. In a world where the ozone layer is already under stress, this is not a trivial consideration. As the morning of September 2nd advanced toward midday in Europe, and the storm's main phase reached its peak intensity, the situation in the European telegraph networks was, if anything, worse than in North America. The European networks had some structural differences from the American ones that affected how the storm's induced currents expressed themselves. The British network, the most extensive in Europe, used a variety of different cable types and routing configurations. Some lines ran along railway corridors, some were buried underground. Some used different gauge wire and different insulation materials. In general, buried cables were significantly less affected than overhead lines. The soil provided some shielding against the rapidly changing magnetic field. But the vast majority of Victorian telegraph infrastructure was overhead wire, and overhead wire was essentially The Electric Telegraph Company's detailed records from September 2, 1859, preserved in the British National Archives and examined by historians of technology including Ewan Rhys-Morris of Aberystwyth University, show a pattern of failures that began in the early morning hours and cascaded through the network as the storm intensified. By 10 in the morning London time, the company was effectively unable to guarantee service on any of its trunk routes. This was not just a commercial problem. The British telegraph network carried official government dispatches, military communications, stock exchange information, and the news wire services that fed the major newspapers. When the network went down, all of these flows of information stopped simultaneously. The Times of London, on September 3rd, would carry a front-page account of the aurora and the telegraph disruptions that is a remarkable document of Victorian scientific journalism, accurate in its description of events, appropriately cautious in its causal explanations, and deeply serious in its assessment of the implications for commercial and governmental communication. But on the morning of September 2nd itself, as the storm raged and the lines went dead, there was no official explanation and no official reassurance. There was just the failure. By early afternoon on September 2nd, Greenwich time, roughly 12 hours after the initial impact and 7 to 8 hours into the main phase of the storm, the situation was beginning, very gradually, to change. The geomagnetic storm had not ended. It would continue, at varying levels of intensity, for another day and a half before the CME had fully passed and Earth's magnetosphere began its slow recovery. But the most extreme peak of the main phase, the period of maximum magnetic field depression, maximum auroral electrojet intensity, maximum induced current in surface conductors, was, by most reconstructions, somewhere around the middle of the day on September 2nd. After that peak, the storm did not end abruptly. It eased, slowly, unevenly, with continued fluctuations and secondary intensifications. The recovery phase of a major geomagnetic storm can take many hours to days, as the magnetosphere slowly expels the excess energy it has absorbed and the ring current gradually decays. But the worst of the induced currents began to ease in the afternoon hours. Some telegraph lines that had been completely dead since before dawn were able to carry limited traffic by late afternoon. The sparking and the electrical shocks became less frequent. Operators who had evacuated their stations began, cautiously, to return. The network was not restored. It was not functioning normally, but it was no longer actively trying to electrocute the people operating it. And as the immediate crisis of the storm's peak began to ease, something important happened. People started to talk about what they had just experienced. The conversations that began in telegraph offices, in newspaper editorial rooms, in scientific societies, and in the correspondence columns of technical journals in the days and weeks after the Carrington event are, in many ways, more important than the event itself. Because in those conversations, the seeds of the modern science of space weather were planted. Not immediately, not cleanly. The process was slow and uneven, full of wrong turns and missed connections. The full theoretical framework for understanding solar-terrestrial relationships, the physics of the solar wind, the magnetosphere, the ionosphere, the induction of ground-level currents, would not be developed for another century. But in September and October of 1859, the right questions began to be asked. What was the connection between the sunspot observations of Carrington and Hodgson and the magnetic storm that followed? What was the mechanism by which disturbances on the sun could affect electrical equipment on Earth? Could such events be predicted? Could their effects on telegraph systems be mitigated? The British Association for the Advancement of Science held discussions. The Royal Astronomical Society published the accounts of Carrington and Hodgson alongside each other, inviting comparison. The American Telegraph magazine ran detailed accounts from operators across the network, building a picture of how the disruption had spread and evolved. The scientific community of the Victorian era was, in its way, attempting to do what modern space weather scientists do as a matter of professional routine: understand the event, reconstruct the mechanism, and think about how to be better prepared next time. The tragedy, and it is a tragedy when you look at it from the perspective of the 21st century, is that the lesson was not fully learned. The telegraph networks of the 1860s and 1870s were rebuilt and expanded without fundamental changes to their vulnerability to geomagnetic storms. The events of 1859 were discussed, catalogued, and filed away in the annals of scientific curiosity. Minor improvements were made to equipment grounding and protection, but the fundamental architecture of long conducting lines, sensitive instruments, and no protection against induced currents remained unchanged. And the world continued to build. More wires, more connections, more dependency on electrical infrastructure. The telephone, the power grid, the radio, the internet, GPS, satellites. Each new layer of technology, more powerful, more useful, and in many cases, more vulnerable than the last. As the sun set on September 2, 1859, and the worst of the storm's main phase eased, the aurora continued. It would continue for several more nights, diminishing but still extraordinary by any normal standard, still reaching latitudes far lower than typical. The magnetosphere was still disturbed. The ring current was still elevated. The slow recovery of Earth's magnetic environment would take days, but the immediate crisis was passing. In the telegraph offices of Boston and New York and London and Paris, exhausted operators were sending the first reliable dispatches in more than 12 hours. News of the storm itself, of the aurora, of the telegraph failures, of the shocks and the sparks and the impossible messages sent by auroral current alone, was beginning to move through the very networks that the storm had just devastated. The story was going out to the world, and Richard Carrington, at his observatory in Surrey, was writing up his notes from the previous morning's observation with the careful precision that was his professional trademark. He had seen a white flare on the face of the sun. He had noted the position, the time, the duration, the intensity. He had gone to find a witness and found one, a neighbor who confirmed the observation. He had measured the magnetic disturbance that his instruments recorded in the hours following the flare. He had, without knowing it, documented the opening moment of the most powerful solar storm in the history of modern civilization. And in his published account, he drew back from the obvious conclusion with a care that was both intellectually honest and, in retrospect, somewhat heartbreaking. "One swallow," he wrote, "does not make a summer." He was right to be cautious. That is what good science requires. But the swallow had come. It had come with terrible force, and it would come again. The only question, then and now, is whether we will be ready when it does. What science now knows. Let us step back from 1859 for a moment. Not to leave it behind, we will return. There is still the question of the full aftermath, the political and scientific response, the legacy of the event across the decades that followed. We will get to all of that. But at this point in the story, we need to do something that the people of 1859 could not do. We need to look at what actually happened. not as Victorian natural philosophers peering at magnetometer traces and burnt telegraph equipment, trying to reason their way toward an explanation with no theoretical framework to guide them, but as 21st century scientists who understand, in precise mathematical detail, the physics of what attacked the planet on September 2nd, 1859. Because the science that has been built up in the century and a half since the Carrington event is extraordinary. It is one of the great achievements of modern physics and space science, and it completely transforms how you understand what you just watched happen in the previous 5 chapters. Let us start with the Sun itself. The modern understanding of solar activity, of how and why the Sun produces flares and coronal mass ejections, of how those events relate to the solar cycle, of what determines their strength and direction, is built on decades of observations from ground-based telescopes, from space missions, and from the painstaking theoretical work of plasma physicists and magnetohydrodynamicists around the world. The Sun's activity is driven by its magnetic field, and the Sun's magnetic field is generated by the motion of electrically conducting plasma in the solar interior, specifically by the differential rotation of the Sun, which rotates faster at the equator than at the poles, and by the convective motions that carry heat from the deep interior to the. These motions stretch, twist, and amplify the magnetic field over time, building up regions of intense magnetic stress, particularly in the sunspot groups that mark areas where strong magnetic field lines are punching through the solar surface. The energy stored in these stressed magnetic configurations can be released suddenly in what physicists call magnetic reconnection events, producing the explosive outbursts we call solar flares and coronal mass ejections. The roughly 11-year solar cycle, the period over which sunspot numbers wax and wane, from solar minimum to solar maximum and back, reflects the underlying cycle of magnetic field buildup and release in the solar interior. Near solar maximum, when the Sun's magnetic field is most complex and most stressed, the rate of major flares and CMEs is highest. The Carrington event occurred during solar cycle 10, one of the stronger solar cycles of the 19th century, which reached its maximum in late 1860. The active region that produced the Great Flare of September 1st was, by every historical account, one of the largest and most complex sunspot groups observed in the entire century. Modern solar physicists, using the magnetographic and helioseismic tools that did not exist in Carrington's time, can now characterize sunspot groups with extraordinary precision, measuring their magnetic flux, their field complexity, their potential energy storage, their probability of producing major flares. The techniques developed by researchers at institutions including the National Solar Observatory, the Royal Observatory of Belgium, and the Lockheed Martin Solar and Astrophysics Laboratory have transformed our ability to monitor and, to some degree, forecast solar activity. But the fundamental physics that drives major events like the Carrington flare has not changed. The Sun is still doing what it has always done. The question of when the next Carrington-scale event will occur is, at its core, a question about the statistics of magnetic field configurations in a turbulent, convecting plasma, which is to say, it is genuinely difficult to predict with precision. What modern science has done, with remarkable success, is reconstruct the Carrington event itself in quantitative detail. The key tool for this reconstruction has been ice cores. In the permanent ice sheets of Greenland and Antarctica, the snow that falls each year becomes compacted into a layer of ice that preserves a chemical record of the atmosphere at the time of deposition. By drilling deep into these ice sheets and extracting long cores, scientists can read a year-by-year record of atmospheric composition going back hundreds of thousands of years. Among the chemical signals preserved in ice cores are nitrate concentrations, and specifically, the enhanced nitrate deposits produced by major solar energetic particle events. When the Sun fires a major CME, it also accelerates protons to very high energies. These are the solar energetic particles that can cause radiation hazards for astronauts and high-altitude aircraft crews. When these high-energy protons reach Earth, they penetrate deep into the polar atmosphere and trigger chemical reactions that produce nitrogen oxides, which eventually deposit as nitrates in the snow. The nitrate spike in Greenland ice cores, corresponding to September 1859, is one of the largest ever identified. Research published by Raymond Muschler and colleagues at Lund University and by Kenneth McCracken and colleagues in the Journal of Geophysical Research has used these nitrate records to estimate the fluence, the total energy, of the solar energetic particle event associated with the Carrington CME. Their estimates suggest it was the largest such event in at least the last 500 years, and possibly much longer. Beryllium-10 records from the same ice cores provide a complementary line of evidence. This isotope is also produced by energetic particle bombardment of the atmosphere, and its enhanced concentration in the 1859 layer is consistent with the nitrate data. The picture that emerges from the ice core record is of a solar energetic particle event significantly more powerful than anything in the instrumental record, more powerful than the great solar proton events of July 1946, of February 1956, of August 1972, of October 2003. More powerful, potentially, than any event in the last millennium. But ice cores are not the only way modern science has approached the Carrington event. The historical magnetometer records, which survive at multiple observatories around the world, have been subjected to modern analysis using techniques that were not available to the Victorian scientists who made the original measurements. The key parameter that modern space weather scientists use to characterize geomagnetic storm intensity is the DST index, the Disturbance Storm Time Index, which measures the depression of the horizontal component of Earth's magnetic field at low-latitude observatories. The DST index was only formally defined in the 1960s, but it can be calculated retrospectively from historical magnetometer records. Estimating the DST for the Carrington event from the surviving Victorian magnetometer data is technically challenging. The instruments of 1859 were less precise than modern ones, and many of them went off-scale during the worst of the storm, which is exactly the problem you do not want when you are trying to measure peak intensity. But the work has been the most widely cited estimate, published by Tsurutani and colleagues in the Journal of Geophysical Research in 2003, suggested a DST of approximately minus 1,700 nanoteslas. This would make the Carrington event roughly 4 to 6 times more intense than the most severe geomagnetic storms of the modern instrumental record, which include the Great Storm of March 13, 1989, which caused a 9-hour blackout across the entire province of Quebec, affecting more than 6 million people, and the Halloween storms of late October 2003, which damaged or destroyed multiple satellites and caused power system problems across northern Europe. More recent work has suggested that the minus 1,700 figure may be an overestimate, with some revised analyses placing the DST in the range of minus 800 to minus 900 nanoteslas. The debate continues in the scientific literature. But even the more conservative estimates place the Carrington event well beyond the range of any storm in the modern instrumental record. As Ying-D Liu of the National Space Science Center in Beijing and colleagues noted in a paper published in Nature Communications, the Carrington event represents a hard upper bound on geomagnetic storm intensity. Or, more precisely, it represents the lower bound of what we know is physically possible. The Sun has done this before. It can do it again. Now let us talk about frequency, because this is where the science gets genuinely alarming. How often does the Sun produce Carrington-scale events? The honest answer is, we do not know precisely. The instrumental record of solar activity is only about 150 years old, barely enough to sample a handful of solar cycles. The ice core and cosmogenic isotope record extends much further, but the time resolution becomes coarser the further back you go, making it hard to identify individual events with confidence. What the existing evidence suggests is that Carrington-scale CME events capable of producing geomagnetic storms in the -800 to -1,700 nanotesla range, occur with a frequency of perhaps once every 100 to 200 years on average. The analysis published by Pete Riley in the journal Space Weather in 2012 attracted considerable attention when it calculated the probability of a Carrington-scale event occurring within the following decade at roughly 12%. Riley's methodology was based on fitting a power law distribution to the historical record of CME intensities, essentially extrapolating from the frequency of smaller events to estimate the probability of the large ones. 12% in any given decade. Over a 50-year period, roughly a working lifetime, the probability rises to something in the range of 50 to 60%. This is not a low probability scenario. This is not the kind of event that emergency planners can reasonably dismiss as too rare to prepare for. A 12% probability per decade is higher than the probability of a major earthquake affecting many of the cities that have invested billions of dollars in earthquake preparedness. And there is another data point that has made researchers particularly attentive in recent years: the Miyake event. In 2012, a Japanese researcher named Fusa Miyake, working with colleagues at Nagoya University, published a paper in the journal Nature that identified an extraordinary spike in carbon-14, the radioactive isotope produced in the atmosphere by energetic particle bombardment, in tree rings dating to 774 and 775 CE during the early medieval period. The carbon-14 spike of 774 to 775 CE is approximately 20 times larger than anything in the ice core record from the last 500 years, including the Carrington event. 20 times larger. The cause of the Miyake event, named for its discoverer, is still debated. The leading hypothesis is an extreme solar energetic particle event, orders of magnitude more powerful than the Carrington storm. Other hypotheses include a gamma-ray burst from a nearby magnetar, though the geometry and probability of such an event are problematic. Most researchers in the field now favor the extreme solar event interpretation, supported by a second Miyake scale event identified in tree rings from 993 CE. What this means, if the solar interpretation is correct, is that the Carrington event, already off the scale of modern experience, is not the upper limit of what the Sun can produce. There may be events in the Sun's repertoire that make Carrington look moderate. This is a sobering thought. it is one that the space weather community takes very seriously. And it is one that should be in the background of any serious discussion of civilizational risk from space weather. Let us now turn to the specific physics of what a Carrington-scale CME does to modern technological infrastructure, because this is where the science becomes directly relevant to the question of contemporary vulnerability. Modern power grids are, in many ways, even more vulnerable to geomagnetically induced currents than Victorian telegraph networks were. The mechanism is the same. Changing magnetic fields induce electrical currents in long conducting structures. But modern high-voltage power transmission lines are in some ways better antennas for these induced currents than Victorian telegraph wires. They are longer. Modern high-voltage transmission lines routinely run for hundreds of miles between substations. They carry much higher voltages, and the transformers that are critical nodes in power grids are susceptible to damage from relatively small amounts of induced direct current flowing through their windings. This last point is crucial and deserves careful explanation. High-voltage power transformers are among the most critical and most difficult to replace components of a modern power grid. A large power transformer, the kind used at high-voltage transmission substations, can weigh anywhere from 100 to 800 tons. It takes specialized factories, many of which are located in a small number of countries, to build them. It typically takes 12 to 18 months to manufacture a large, custom power transformer from order to delivery. And the global spare transformer inventory is, in normal times, quite limited. During a severe geomagnetic storm, the geomagnetically induced currents that flow through power grid conductors enter transformers as quasi-direct currents, currents that have a very low frequency, essentially direct current from the transformer's perspective. And even small amounts of direct current flowing through a transformer winding cause a phenomenon called half-cycle saturation, in which the transformer's magnetic core is driven into saturation on alternate half-cycles of the alternating current it is designed to handle. The consequences of half-cycle saturation are serious. The transformer generates massive amounts of reactive power, drawing extraordinary currents from the grid. It produces intense vibration in its core. It generates heat rapidly and in large amounts in a device that is already operating near its thermal limits under normal conditions. In a severe enough geomagnetic storm, transformers can be destroyed by geomagnetically induced current exposure in a matter of not damaged and repairable, destroyed. Their insulation cooked, their windings shorted, their cores permanently demagnetized in destructive ways. The grid failure in Quebec on March 13, 1989, was caused by exactly this mechanism, operating at a storm intensity of roughly minus 550 nanoteslas DST. The storm drove geomagnetically induced currents into the Hydro-Quebec transmission system, saturated transformers, caused a cascade of relay and protection system trips, and took the entire provincial grid from normal operation to complete blackout in 90 seconds. 90 seconds. From full power to nothing. For a province of 6 million people. The Carrington Event was roughly 3 to 6 times more intense than the Quebec storm, depending on which DST estimate you use. The National Academy of Sciences report on severe space weather events, published in 2008, a landmark document that is sometimes called the Severe Space Weather Report, prepared under the leadership of Daniel Baker of the University of Colorado, estimated that a Carrington-scale geomagnetic storm striking the modern United States power grid could permanently damage or destroy between 300 and 350 extra high-voltage transformers in the first few hours. 300 to 350 large transformers simultaneously destroyed, with a global manufacturing capacity of perhaps a few dozen per year. The same report estimated that restoring power to the worst affected regions of the United States after such an event could take between 4 and 10 years. 4 to 10 years without reliable electricity. The report was careful to note the uncertainties in these estimates. They depend on assumptions about storm geometry, grid configuration, transformer susceptibility, and other factors that are genuinely hard. But the qualitative conclusion that a Carrington-scale event represents an existential threat to modern electrical infrastructure is not seriously disputed in the space weather community. What about satellites? In 1859, there were no satellites. The sky was empty of human-made objects. The storm's effects on the upper atmosphere, the extraordinary heating and expansion of the thermosphere, the disruption of the ionosphere, the particle bombardment of everything above the protective layers of the atmosphere, had no technological consequences because there was no technology there to be affected. Today, there are roughly 8,000 active satellites in orbit around Earth. They include the GPS constellation, which provides positioning, navigation, and timing services that the modern economy depends on in ways that most people never think about, not just for finding directions, but for synchronizing financial transactions, for timing power grid operations, for navigating ships and aircraft. They include the weather satellites that provide the data for meteorological forecasting. They include the communication satellites that carry internet traffic, telephone calls, and television broadcasts to billions of people. They include the Earth observation satellites that monitor agricultural conditions, track deforestation, watch for wildfires and floods. In a Carrington-scale event, every satellite in low Earth orbit faces multiple simultaneous threats. First, atmospheric drag. During a major geomagnetic storm, the upper atmosphere, the thermosphere, at altitudes of roughly 90 to 600 kilometers, is heated enormously by the particle precipitation and Joule heating associated with the storm. This heating causes the thermosphere to expand dramatically, increasing its density at the altitudes where low Earth orbit satellites fly. The increased atmospheric density means increased drag on the satellites. They lose altitude faster. The effect on individual satellites is small in absolute terms, but for the operators who need to maintain precise orbital positions, particularly for GPS and other navigation constellation satellites, the unexpected orbital perturbations are a serious operational challenge. The most dramatic demonstration of this effect in the modern era came not from a geomagnetic storm, but from the solar storm of February 3 to 4, 2022, when a relatively modest CME impacted Earth just as SpaceX was deploying a batch of 49 Starlink satellites into a low staging orbit. The enhanced atmospheric drag associated with the geomagnetic storm caused 40 of the 49 satellites to re-enter the atmosphere and burn up before they could be raised to their operational altitude. 40 satellites lost in a single event, in a storm that was orders of magnitude less powerful than Carrington. Second, satellite charging. During a geomagnetic storm, the flux of energetic electrons in the outer radiation belts can increase by factors of hundreds to thousands. These electrons can penetrate satellite surfaces and charge up internal components, causing electrostatic discharges, essentially lightning bolts inside the satellite's electronics, that can destroy components or cause the satellite to fail entirely. Third, direct radiation damage to electronics. The solar energetic particles associated with a major CME event, the high-energy protons that leave the sun in the hours after the flare, can penetrate deep into satellite shielding and cause what is called single-event upsets in digital electronics, bit flips and logic errors that can corrupt software, disable systems, or in worst cases, cause permanent hardware damage. The combination of these effects, enhanced drag, electrostatic charging, and direct radiation damage, means that a Carrington scale event would be likely to damage or destroy a substantial fraction of the satellite constellation in low Earth orbit. Estimates vary because the specific effects depend on satellite design, orbit altitude, orientation, and other factors. But the qualitative picture is consistent across analyses by researchers at institutions including the Aerospace Corporation, the Johns Hopkins Applied Physics Laboratory, and the European Space Agency's Space Environment Effects Group. A Carrington scale event would be the worst day in the history of the space industry by an enormous margin. There is one more technology we need to discuss here, because it is one that did not exist in 1859 and whose vulnerability to geomagnetic storms is often underappreciated: the Internet. The Internet is not a wireless system. It is overwhelmingly a physical infrastructure of fiber optic cables, copper cables, and the electronic equipment, routers, switches, amplifiers, data centers, that connects them. Most of this infrastructure is powered by the electrical grid. If the grid goes down, the Internet goes down with it, everywhere that has lost power. But there is a more subtle vulnerability that has been explored in detail by researchers including Sangeetha Abdu-Jyothi of the University of California, Irvine, whose work on solar superstorm risk to Internet infrastructure attracted significant attention when it was published in 2021. Long-distance submarine cables, the fiber optic cables that carry the vast majority of international Internet traffic across the ocean floors, use repeater systems to amplify signals every 50 to 150 km. These repeaters are powered by direct current sent through a conductor in the cable from shore-based power feeding equipment at the cable landing stations. If the power grid fails at the cable landing stations, which are connected to the local grid just like any other facility, the submarine cables lose their power feed and stop working. The fiber itself is unaffected, but the repeaters go dark, and the cable becomes effectively non-functional for long-distance communication. This means that a Carrington scale event affecting power grids in multiple countries simultaneously, which is exactly what such an event would do, could take down not just domestic Internet infrastructure, but the international backbone that connects continents to each other. The scenario that emerges from this analysis: grid failures cascading into Internet infrastructure failures, satellite losses, degrading GPS and satellite communication, compass navigation disrupted at sea, aviation potentially grounded due to GPS dependency and communication failures, is one in which the interconnected technological civilization of the 21st century finds itself, suddenly and without warning, substantially cut off from the real-time information flows it depends on for everything from financial transactions to hospital operations to water treatment. This is not catastrophizing. This is the sober assessment of engineers, physicists, and emergency planners who have looked carefully at the numbers. And the numbers say that this is not a question of if, it is a question of when. But here is something important, something that tends to get lost in the alarming cascade of failure scenarios. We know this is coming. We have known it with increasing precision and confidence for decades. And knowing it is coming means we have the option, the technical capability, the engineering knowledge, the institutional capacity to prepare. The science of space weather forecasting has advanced enormously since the days of Richard Carrington. The physics of geomagnetic storms is understood in detail. The engineering of grid protection against geomagnetically induced currents is well developed. There are systems, already deployed in some countries, that can detect the onset of induced currents and protect transformers by taking them temporarily offline before damage occurs. The design of radiation-hardened satellites, capable of surviving the worst of a solar energetic particle event, is established technology. The question of whether civilization will be ready for the next Carrington event is not fundamentally a scientific question. The science is done. The physics is known. It is a political and economic question. A question of whether governments and industries will invest now in the protection of infrastructure whose failure would be civilizational in scale. A question of whether the low annual probability of a catastrophic event, even a 12% per decade probability, is enough to motivate action in a political system that typically struggles to address risks that are not immediate and visible. Those are the questions, and they are, frankly, more difficult than any of the physics. Aftermath, legacy, and the world that wasn't ready. In the days after the storm, the world tried to make sense of what had happened. It did not entirely succeed. The immediate practical task was restoration. The telegraph companies of North America and Europe, the Electric Telegraph Company in Britain, Western Union and its competitors in the United States, the state telegraph administrations of France, Prussia, Austria, and Russia, spent the days following September 2nd assessing damage, repairing equipment, replacing burned instruments, and cautiously restoring service on their most critical. The physical damage in most cases was less severe than the chaos of the storm's peak hours had suggested it might be. The Carrington event had not melted telegraph wires or physically destroyed cable infrastructure on a massive scale. What it had done was overwhelm the sensitive electrical instruments at both ends of those cables: the galvanometers, the recording devices, the relay mechanisms, with currents far beyond their design tolerances. Many instruments were burned out. Some relay stations had suffered fire damage, but the wire itself, the physical backbone of the network, was largely intact. This meant that restoration was measured in days and weeks, not months and years. By September 5th and 6th, most major telegraph routes in the United States and Britain were carrying traffic again, at least sporadically. By the end of September, the networks were largely functional, though with reduced capacity in some areas where equipment replacement was still underway. The financial cost was significant but not crippling. The telegraph companies absorbed the losses, repaired or replaced the damaged equipment, and resumed operations. There was no government bailout, no emergency legislation, no formal inquiry with the force of law behind it. The companies simply got on with the work, and in getting on with the work, without pausing long enough to fundamentally reconsider the vulnerability of what they were rebuilding, they made a choice, perhaps unconsciously, perhaps inevitably, given the commercial pressures of the time, that would echo forward through the decades. They rebuilt the same system. The scientific response was more interesting and more nuanced than the commercial one. In the weeks and months after the Carrington event, the pages of scientific journals on both sides of the Atlantic filled with accounts, analyses, and theoretical speculation. The volume of material published in response to the event was, by the standards of Victorian scientific publishing, extraordinary. It reflected genuine excitement, the sense that something important had happened, that nature had revealed a phenomenon that demanded explanation. Richard Carrington's paper, published in the monthly notices of the Royal Astronomical Society in November 1859, is the document that established his permanent place in the history of solar science. It is a model of Victorian scientific precision, detailed, quantitative, carefully qualified, scrupulously honest about the limits of what could be concluded from the available evidence. Carrington described the white flares he had observed on September 1st. He documented their position on the solar disk, their duration, their intensity relative to the solar surface. He noted the magnetic disturbance that his instruments recorded in the hours following the observation. And then he did something that speaks well of him as a scientist. He explicitly declined to assert a causal connection between the flare and the magnetic storm, on the grounds that a single coincidence, however striking, was not sufficient evidence. One swallow does not make a summer. Richard Hodgson's independent confirmation of the flare observation was published alongside Carrington's paper, strengthening the observational case considerably. The editors of the monthly notices clearly understood that they were publishing something historically significant. The papers were given prominent placement and were accompanied by editorial commentary emphasizing their importance. The broader scientific community engaged seriously with the question of solar-terrestrial relationships in the aftermath of the event. Edward Sabine, the Irish geophysicist who had been studying the relationship between sunspot numbers and geomagnetic activity for more than a decade, saw in the Carrington event powerful support for his thesis that solar activity and Earth's magnetic field were connected. Sabine had already established, from statistical analysis of magnetic observatory records, that geomagnetic disturbance correlated with the sunspot cycle. The Carrington event, with its precisely documented solar observation and its accompanying magnetic storm, was, for Sabine, a dramatic confirmation of what he had been arguing for years. But Sabine's statistical correlation was not a causal mechanism. It established that the Sun and Earth's magnetic field were connected in some way. It did not explain how. And in 1859, with no understanding of the solar wind, no concept of the magnetosphere, no theory of plasma physics, the field did not yet exist. Filling that explanatory gap was simply beyond the reach of available science. The theoretical framework would come, but it would come slowly, built up over the following century through the contributions of dozens of researchers working in parallel on different pieces of the puzzle. George Fitzgerald in the 1880s suggested that solar eruptions might be connected to geomagnetic storms through some kind of electromagnetic disturbance propagating through the ether. Christian Birkeland, the Norwegian physicist whose polar expeditions in the early 1900s produced extraordinary observations of auroral phenomena, proposed that streams of charged particles from the Sun were responsible, a remarkably prescient insight, made decades before the physics to support it was available. It was not until the 1950s that Eugene Parker, at the University of Chicago, developed the theoretical framework for the solar wind, the continuous outflow of plasma from the Sun that fills the solar system and carries the Sun's magnetic field into interplanetary space. Parker's solar wind theory, published in 1958, was initially met with skepticism by many in the scientific establishment. It was confirmed by direct measurement just 4 years later, when the Soviet Luna 1 spacecraft and then the American Mariner 2 mission to Venus detected the solar wind in situ. The magnetosphere, the region of space dominated by Earth's magnetic field, was also first mapped in the late 1950s and early 1960s using data from the early Explorer satellites and the work of James Van Allen at the University of Iowa, whose discovery of the radiation belts that bear his name was one of the landmark results of the International Geophysical Year of 1957 to 58. By the 1960s, the basic physical picture was in place. The sun emits a continuous solar wind. Large eruptions, CMEs, produce dramatic enhancements of the solar wind. These enhancements interact with Earth's magnetosphere, driving geomagnetic storms. The storms induce electrical currents in the ionosphere and on the ground. The circle from Carrington's observation to a complete physical theory took roughly 100 years to close. In the meantime, the world had not been standing still. The decades after the Carrington Event saw the most rapid technological transformation in human history. The telegraph networks of 1859 were modest compared to what came next. The telephone, invented by Alexander Graham Bell in 1876, created a new layer of electrical communication infrastructure. The development of commercial electric power in the 1880s, Thomas Edison's direct current systems, and Nikola Tesla and George Westinghouse's alternating current systems, created power grids that were, from the beginning, vulnerable to geomagnetically induced currents in ways that nobody fully appreciated at the time. The power grid introduced something qualitatively new to the equation of geomagnetic vulnerability: the possibility of catastrophic, simultaneous, widespread failure affecting not just communication, but the physical infrastructure of modern civilization. A telegraph network that goes down is an inconvenience, even a serious one. A power grid that goes down takes hospitals off life support, stops water treatment plants, shuts down food refrigeration, disables heating and cooling systems, and cuts off the electronic infrastructure that the modern economy depends on for every transaction. The first major geomagnetic storm to significantly affect a power grid occurred not in 1859, but in May 1921, an event sometimes called the New York Railroad Storm, or the Carrington Event's little brother, which produced a DST estimated at roughly -900 nanoteslas. The storm caused fires at telegraph and telephone exchanges in several locations, disrupted telegraph and telephone service across much of the northeastern United States and northern Europe, and caused a fire in the control tower of the New York Central Railroad at 57th Street in Manhattan. It was a serious event. But the power grids of 1921 were simpler, more localized, and more resilient than modern grids. There were fewer long-distance, high-voltage transmission lines, fewer interconnections, fewer of the large, high-voltage transformers that are the critical vulnerability in modern grid design. The next major demonstration of power grid vulnerability came in 1989. The Quebec blackout of March 13, 1989, is the event that finally forced the power industry to take geomagnetic risk seriously. The storm, associated with a major CME from solar cycle 22, struck Earth's magnetosphere and drove intense geomagnetically induced currents through the Hydro-Quebec transmission system. The currents saturated static VAR compensators and transformers, causing a cascade of protection system trips that took the entire provincial grid from normal operation to total blackout in 90 seconds. 6 million people lost power. The blackout lasted 9 hours for most customers, longer for some. Several large power transformers were damaged. The economic cost, including damage to the grid infrastructure and lost industrial production, ran to hundreds of millions of dollars. The Quebec blackout was a wake-up call. It demonstrated, concretely and undeniably, that geomagnetic storms could cause large-scale power grid failures in the modern electrical system. It prompted the power industry, particularly in North America, to begin serious research into geomagnetically induced current effects and mitigation strategies. The North American Electric Reliability Corporation, known as NERC, which is the regulatory body responsible for the reliability of the North American bulk power system, began developing standards and guidelines for geomagnetic storm preparedness. Research programs at utility companies, national laboratories, and universities around the world began working on the problem of transformer protection, grid hardening, and operational procedures for managing severe geomagnetic events. Progress was made. Real, important progress. Monitoring systems were improved. Operating procedures were. Some utilities installed blocking devices on transformer neutral connections. Hardware that prevents the quasi-direct induced currents from entering transformer windings while allowing normal alternating current to flow freely. But the progress was uneven. The grid hardening that has been done represents a fraction of what the most vulnerable components of the North American, European, and Asian power infrastructure would require to be reliably protected against a Carrington-scale event. There is a pattern here that is worth naming explicitly. Every time a major geomagnetic storm occurs, 1859, 1921, 1989, 2003, there is a period of intense interest, research, and concern. Reports are written, conferences are held, standards bodies propose new requirements, utilities make some investments in protection. And then the storm passes, the immediate concern fades, and the pace of preparation slows. This pattern, intense response followed by gradual complacency, is well documented in the disaster preparedness literature. It applies to earthquakes, to floods, to pandemics, to industrial accidents. Human beings and human institutions are, in general, much better at responding to disasters that have just happened than at preparing for disasters that have not happened yet. The Carrington event is, in some ways, both the worst and the best example of this pattern. Worst because it happened in 1859, long enough ago that institutional memory of it has faded almost entirely outside the specialist community. Best because the physical record of it is preserved in the ice cores and the magnetometer traces and the newspaper accounts, and because the scientific community has spent decades carefully documenting exactly what happened and what it would mean if it happened today. The knowledge exists. The science is done. The engineering solutions are not. What remains is the will to implement them. Let us now do what the scientists and engineers who have studied this problem have done. Let us construct the timeline of a modern Carrington event, not as a science fiction scenario, as a careful extrapolation from established physics, documented engineering vulnerabilities, and the lessons of previous, smaller events. The date is arbitrary. The physics is not. The event begins, as it did in 1859, with a solar flare. A large, complex sunspot group near the center of the solar disk, positioned so that any CME it fires will be aimed directly at Earth, produces an X-class flare. The X-class designation is the highest in the modern flare classification system, reserved for flares with peak X-ray flux above 10 microwatts per square meter at Earth's distance from the Sun. The largest flares ever recorded during the Halloween storms of 2003 were estimated at X45 or higher before the instruments measuring them went off scale. The flare of our hypothetical event is large, very large. 8 minutes and 20 seconds after the flare fires, the X-ray pulse arrives at Earth. The dayside ionosphere is strongly ionized. High-frequency radio communications, shortwave radio, which is used by aviation, maritime services, military communications, and amateur radio operators worldwide, experience a sudden ionospheric disturbance. For roughly an hour, HF radio on the day side of the planet is significantly degraded or completely blacked out. Simultaneously, the solar energetic particles, protons accelerated to relativistic speeds by the shock ahead of the CME, begin arriving. Within 30 minutes to a few hours of the flare, depending on the particle energies involved, a solar proton event is underway. High-altitude aircraft on polar routes receive radiation doses that exceed safe limits for crew members. Aviation authorities begin rerouting polar flights to lower latitudes. Satellites in low Earth orbit and in medium Earth orbit, including the GPS constellation, begin experiencing increased radiation. The GPS satellites, flying at roughly 20,000 kilometers altitude in the heart of the outer radiation belt, are in a particularly challenging environment. Navigation accuracy begins to degrade as the satellite electronics respond to the radiation environment. Space weather centers, the NOAA Space Weather Prediction Center in Boulder, Colorado, the European Space Weather Service Network, the Japanese National Institute of Information and Communications Technology, issue their highest-level alerts. A KP index of 9, the maximum on the standard scale of geomagnetic activity, is forecast. Utilities, pipeline operators, and satellite operators are notified. This is the opening act. It unfolds over the first hour after the flare. Approximately 15 to 40 minutes before the CME arrives at Earth, when it passes the L1 monitoring point, roughly 1.5 million kilometers sunward of Earth, the Discover satellite detects the shock front. The solar wind speed reading jumps dramatically. The magnetic field sensor shows the interplanetary magnetic field turning strongly southward. Southward. The worst possible orientation. The orientation that opens the magnetosphere. The space weather forecasters see this data in real time. They know what it means. The CME will arrive at Earth in 15 to 40 minutes, and it is carrying a strongly southward magnetic field. The alerts go out immediately. Emergency notifications to power grid operators, to satellite operators, to pipeline companies, to aviation authorities, to military space operations centers. Everything that can be done in 15 minutes to protect vulnerable infrastructure is attempted simultaneously. Power grid operators in the most vulnerable regions, the northern United States, Canada, Scandinavia, the United Kingdom, northern Russia, begin emergency procedures. Some try to reduce power flows on vulnerable transmission lines. Some attempt to bring additional reactive power compensation online. Some begin the process of manually tripping certain high-voltage transformers offline to protect them from induced current damage, a procedure that requires careful coordination and that, if done incorrectly, risks cascading failures of its own. 15 minutes is not enough time to do all of this correctly across a grid as complex and geographically vast as the North American interconnection. Some transformers are protected. Many are not. The CME arrives. The sudden storm commencement is registered simultaneously at magnetic observatories around the world. A sharp, simultaneous spike in the horizontal magnetic field component as the CME's shock front compresses the magnetosphere. The compression is severe. The magnetopause, the boundary of Earth's magnetic shield, is pushed inward toward the planet. In low Earth orbit, the Starlink constellation, the International Space Station, and hundreds of other spacecraft experience a sudden increase in atmospheric drag as the thermosphere begins to heat and expand. Satellite operators begin receiving automatic alerts from their attitude control systems as orbits start to decay faster than nominal. On the ground, the first induced currents appear in long conductors within seconds of the sudden storm commencement. They are modest at first, a few amperes in long transmission lines, a slight deflection in pipeline monitoring systems. But the geomagnetic field is still changing. The storm is just beginning its main phase. In the first 30 minutes after impact, the situation escalates rapidly. The geomagnetic field at high latitudes is Magnetometers in Scandinavia, Canada, Alaska, and Siberia are recording rates of change in the horizontal magnetic field component that exceed 100 nanoteslas per minute, values seen only during the most extreme historical storms. At some stations, the rate of change briefly exceeds 500 nanoteslas per minute. These rates of change translate directly into induced voltages in surface conductors. A transmission line running 500 kilometers in the right orientation is experiencing induced voltages of hundreds of volts. The currents flowing into transformer neutral connections are reaching tens, then hundreds of amperes. The transformers begin to saturate. In the control rooms of major power utilities across the northern United States and Canada, alarms are going off simultaneously on multiple systems. Voltage is dropping on transmission lines. Reactive power demand is spiking. Automatic protection relays, the devices that are supposed to protect grid equipment from damage by disconnecting it from the grid when something goes wrong, are beginning to trip. Some of these trips are protective and deliberate. Others are the cascading consequence of voltage instability. Relays tripping because the voltage they are monitoring has dropped below threshold, because other relays upstream have already tripped, because the grid is losing its ability to balance supply and demand across its vast interconnected network. The cascade begins. It does not happen everywhere at once. The storm's effects are concentrated at high latitudes first, spreading toward lower latitudes as the geomagnetic disturbance intensifies. The first major grid failures occur in Canada and the northern tier of the United States: Minnesota, Wisconsin, Michigan, New York, New England. Within the first hour after CME impact, large portions of these regions have lost power. The cascade spreads south. The loss of generation and transmission capacity in the north creates voltage and frequency instability that propagates through the grid like a wave. Automatic protection systems, doing exactly what they were designed to do, disconnect vulnerable equipment to prevent damage. But in doing so, they accelerate the collapse of the grid they are designed to protect. By 2 hours after impact, the northeastern United States and most of Canada are dark. The Midwestern grid is failing. The Western interconnection, California, the Pacific Northwest, the mountain states, is struggling to maintain stability as the eastern grid collapses and takes with it the interconnections that allowed power to flow between the two systems. By 3 hours after impact, a substantial fraction of North America is without power. Now the secondary consequences begin. Hospitals switch to emergency generators. Most modern hospitals have backup generation capable of running critical systems, life support, operating theaters, intensive care units, emergency departments, for between 72 hours and 1 week, depending on fuel reserves. For the first few days, the critical care infrastructure holds, but the fuel reserves are finite, and the supply chains that would normally deliver diesel fuel to hospital generators are now severely disrupted. Because fuel delivery depends on electronic payment systems, on GPS navigation, on traffic signal systems, on the communication infrastructure that allows drivers and dispatchers to coordinate. All of these are failing. Water treatment and distribution systems begin to fail within the first few hours in areas without backup generation. Water treatment plants require continuous electrical power to run pumps and chemical treatment systems. Without power, they can run on backup generation for a limited time. But the same fuel supply problem that affects hospitals affects water treatment. In cities that have lost water pressure, fire suppression becomes impossible. In a scenario where the storm has caused electrical fires, from induced current damage in building wiring, from transformer explosions, from the shorting of electrical equipment, the loss of fire suppression capability is catastrophic. Food safety begins to degrade within hours. Modern food supply chains are extraordinarily dependent on continuous refrigeration, from the farm to the processing facility, to the distribution warehouse, to the grocery store, to the home refrigerator. Without power, the cold chain breaks. Perishable food begins to spoil within hours in refrigerators, and within 24 to 48 hours in commercial cold storage facilities. Communication systems begin to fail in stages. Cell towers have backup batteries rated for between 4 and 8 hours of operation without grid power. When those batteries are exhausted, cell service fails. Landline telephone systems, what remains of them, fail similarly as their central office battery backups drain. The Internet backbone, powered by data centers with more substantial backup power, holds somewhat longer. But without grid power to charge devices, and without cell networks for mobile connectivity, the practical ability of most people to access the Internet degrades rapidly. Meanwhile, in orbit, the situation is deteriorating steadily. The radiation environment in low Earth orbit has been intense since the solar energetic particle event began, hours before the CME arrived. The cumulative radiation dose on satellite electronics is building. Some satellites have already experienced anomalies, bit flips in memory, unexpected resets of control systems, degraded performance from solar panel radiation damage. Now, with the full force of the geomagnetic storm driving energetic electrons to extreme fluxes in the outer radiation belt, the electrostatic charging environment around many satellites is at dangerous levels. Charge is building up on satellite surfaces and on insulating materials inside satellite structures. The risk of electrostatic discharge, a sudden destructive spark jumping between charged surfaces inside the satellite's electronics, is high. Some satellites fail. Others enter safe mode, a protective operational state in which non-essential systems are shut down and the satellite waits for the radiation environment to improve. From the outside, A satellite in safe mode looks like a failed satellite. It is not providing its intended service. GPS accuracy is degrading as more satellites in the constellation enter safe mode or experience anomalies. The timing signals that GPS provides, used not just for navigation, but for synchronizing financial transactions, power grid operations, telecommunications networks, and dozens of other critical functions, are becoming unreliable. The aviation system, which has been in various states of disruption since the first HF radio blackout after the flare, is now facing a more fundamental problem. Modern commercial aircraft navigation depends heavily on GPS. Air traffic control depends on GPS-derived position data. As GPS accuracy degrades, the safety margins that modern air traffic management is built on begin to erode. Aviation authorities around the world, the Federal Aviation Administration, Eurocontrol, the Civil Aviation Administration of China, begin grounding flights at airports in the most severely affected regions. Thousands of aircraft that are already in the air are directed to divert to airports where landing is still safe with degraded navigation. The global air transport system, which carries roughly 12 million passengers per day, is shut. By 12 hours after CME impact, the landscape of modern civilization has been transformed. Across the high and mid-latitudes of the Northern Hemisphere, North America, Europe, Russia, Northern Asia, large portions of the population are without electrical power. The financial system has effectively stopped. Electronic payment processing is down. ATM networks are down. Stock exchanges have suspended trading. The Internet, while partially functional in some regions, is inaccessible to most people because their devices are losing charge and their cellular connections have failed. In regions that still have power, lower latitudes, regions with more resilient or better protected grids, the situation is tense but functional. The storm has not been uniform in its geographic effects. The equatorial and mid-latitude regions of the Southern Hemisphere, where the geomagnetic-induced current effects are weaker due to the orientation of Earth's field, are significantly less affected. Parts of South America, Africa, Southeast Asia, and Australia are watching the disaster in the Northern Hemisphere through whatever communication channels remain available. But the global economy is so deeply interconnected that the failure of the North American and European power grids sends shockwaves everywhere. Supply chains that depended on just-in-time manufacturing, on global shipping coordinated by GPS, on financial transactions cleared through New York and London, all of these are disrupted, regardless of whether the local power grid is still running. What happens next depends on choices, human choices, institutional choices, political choices. In the most optimistic scenario, one in which preparation has been adequate, in which spare transformers have been pre-positioned, in which grid operators execute their emergency procedures effectively, in which fuel supplies to critical infrastructure are maintained, the recovery begins within days. Power is restored to the most critical infrastructure first. The grid is rebuilt cautiously, section by section. Within weeks, partial functionality is restored to the most essential systems. Full recovery takes months. In the least optimistic scenario, one in which the most critical transformers have been permanently destroyed, in which the spare inventory is insufficient, in which the cascading failures have damaged not just the large transformers, but the full ecosystem of grid equipment. Recovery takes years. Not 4 to 10 years, as the 2008 National Academy of Sciences report estimated for the United States alone. Possibly longer, if the global manufacturing capacity for replacement transformers is itself disrupted by the storm, and if the social and political systems needed to coordinate recovery are themselves degraded by months without power. The difference between these scenarios is not primarily a matter of luck. It is primarily a matter of preparation. Richard Carrington, who died in 1875 at the age of 49, never knew the full significance of what he had observed on the morning of September 1st, 1859. He knew he had seen something extraordinary on the face of the sun. He suspected, cautiously, that it might be connected to the magnetic storm that followed. He published his observations, maintained his scientific scruples about causation, and continued his work. He never lived to see the telephone, or the power grid, or the radio, or the He never lived to see the world become the kind of wired, interconnected, electricity-dependent civilization that would be most vulnerable to what he had watched happen on the surface of a star 93 million miles away. But in a very real sense, the warning he issued, inadvertently, simply by observing carefully and publishing honestly, is the warning that the modern world is still, 166 years later, deciding how seriously to take. The sun has not changed since 1859. The physics has not changed. The 11-year solar cycle continues. The sunspot groups continue to form and store magnetic energy, and release it in eruptions that send billions of tons of plasma across the solar system at thousands of kilometers per second. We have built a civilization that is more capable, more comfortable, and more vulnerable than anything Richard Carrington could have imagined. And the question of whether that civilization is ready for what the sun can do is still, as of today, March 10, 2026, one of the most important unanswered questions in the management of civilizational risk. Conclusion. The star that remembers. We have come a long way from that September morning in 1859. We have stood in Richard Carrington's observatory in Surrey, watching white light erupt from the face of the sun. We have followed the plasma cloud across 93 million miles of interplanetary space in 17 hours and 40 minutes. We have sat with the telegraph operators of Boston and Washington and London as their instruments tried to kill them. We have watched the sky turn crimson over Georgia and Cuba and Rome, bright enough to read by at midnight, bright enough to wake entire cities from their sleep in the conviction that the world. We have traced the physics, the magnetic reconnection, the auroral electrojet currents, the geomagnetically induced voltages in copper wire. From Victorian natural philosophy, through a century of plasma physics and space science, to the precise mathematical understanding that researchers at NASA and ESA and institutions around the world have built up in the decades since. And we have looked, as honestly as the available science allows, at what that same event would mean for the civilization we have built since then. The picture is not comfortable. It was never going to be comfortable. But before we close, there are things worth saying that often get lost in the disaster scenario narratives. Because the story of the Carrington Event is not just a story about vulnerability and catastrophe. It is also a story about human observation, human curiosity, human persistence, and, if we choose to make it so, human foresight. Let us start with what we have actually learned. The science of space weather, in the century and a half since Carrington watched those white flares appear and disappear in 5 minutes, has become one of the most productive fields in modern geophysics and astrophysics. We understand the solar cycle with a precision that would have seemed miraculous to the Victorian natural philosophers who first identified it. We can monitor the sun's surface continuously, in multiple wavelengths simultaneously, from space-based observatories that never sleep and never have clouds blocking their view. The Solar Dynamics Observatory, launched by NASA in 2010, captures an image of the full solar disk every 12 seconds in 10 different wavelengths of extreme ultraviolet and X-ray light, building a continuous, extraordinarily detailed record of solar activity that would have reduced Richard Carrington to speechless wonder. We can watch CMEs leave the sun in real time. The SOHO spacecraft, the stereo mission, the coronagraph instruments that block out the blinding disk of the sun to reveal the faint structures in the corona. These tools give us a view of the solar wind environment that is qualitatively different from anything available before the space age. We have learned to read the history of the sun in ice. The cosmogenic isotope record preserved in the Greenland and Antarctic ice sheets is a solar activity archive extending back hundreds of thousands of years, allowing researchers to place the Carrington Event in its full historical context, to understand not just that it was extreme, but how extreme, relative to the full range of solar behavior over geological time. We have built the theoretical framework that explains not just what happened in September 1859, but why. The plasma physics of magnetic reconnection, the magnetohydrodynamics of CME propagation, the physics of particle acceleration and radiation belt dynamics, the electrokinetics of geomagnetically induced ground currents. The understanding is not complete. Space weather science remains an active research frontier, with genuine open questions about CME initiation physics, about the mechanisms of extreme solar energetic particle events, about the predictability of the BZ component of arriving CMEs. But the foundational physics is established and robust, and we have built monitoring infrastructure. The L1 monitors, ACE, Discover, and their predecessors, provide the real-time solar wind measurements that drive modern space weather forecasting. Ground-based magnetometer networks from the SuperMag Consortium aggregate data from hundreds of observatories worldwide, providing global coverage of geomagnetic activity in real time. Ionospheric monitoring networks track the upper atmosphere's response to solar events continuously. This is genuine achievement. It represents an enormous investment of scientific talent and public resources over many decades, and it has produced knowledge and capability that would not exist if the scientists and engineers who built it had not persisted through the long periods between major events when the urgency was easy to forget. Now let us talk about what we have not learned, or more precisely, what we know but have not yet fully acted on. The engineering solutions to the most critical vulnerabilities are, in most cases, known. They are not exotic. They are not dependent on technologies that do not yet exist. Transformer protection against geomagnetically induced currents can be achieved through several methods. Neutral current blocking devices, hardware installed at transformer neutral connections to prevent quasi-direct induced currents from entering the windings while allowing normal alternating current operation, are available commercially and have been deployed by some utilities, particularly in Finland and Norway, where the geomagnetic risk is high and the power industry has taken the threat seriously for decades. The cost of equipping the most critical high-voltage transformers in a national grid with these devices is significant. Estimates for the full United States extra high-voltage network run to hundreds of millions to low billions of dollars. But it is trivially small compared to the economic cost of a prolonged grid failure. Operational procedures for managing the grid during geomagnetic storms, reducing power flows on vulnerable lines, pre-positioning reactive power compensation, pre-staging spare transformers, coordinating with neighboring utilities on emergency protocols, can be developed and rehearsed without requiring any new hardware investment. The knowledge to do this exists. The barrier is primarily institutional. Getting the dozens of utilities and regulatory bodies involved in grid operation to coordinate on a threat that may not materialize for decades. Satellite hardening against radiation and electrostatic charging is an established engineering discipline. Radiation-hardened electronics, Faraday cage shielding, active charge management systems. These technologies have been developed and used in military and high-reliability space systems for decades. Applying them to commercial satellite constellations adds cost, but the cost is manageable, and for the operators of large constellations whose business depends on satellite availability, the investment case is straightforward. Communication resilience, the ability to maintain some level of communication capability when the primary infrastructure has failed, has been a concern of military planners and emergency management agencies for decades. High-frequency radio, which was the standard before the satellite era, and which remains functional during geomagnetic storms at frequencies that avoid the disturbed ionospheric layers, is a genuine backup capability that requires relatively modest investment to maintain. The stockpiling of spare extra high-voltage transformers, the single most important resilience measure for the power grid, given the long lead time for manufacturing and the criticality of transformers to grid restoration, has been discussed and advocated by engineering experts and policy analysts for years. Some progress has been made. The United States has made investments in the Spare Transformer Equipment Program, and some individual utilities maintain larger spare inventories than they once did. But the global spare transformer inventory remains, by most expert assessments, inadequate for a Carrington-scale event affecting multiple countries simultaneously. These are solvable problems. They have known solutions. They require money, coordination, and political will, but not scientific breakthroughs that have not yet been made. The gap between what we know and what we have done is, in the end, a human problem, not a technical one. There is something profound in the story of how the Carrington Event has moved through time. In September 1859, it was an experience, something that happened to real people. The telegraph operator who jumped back from his sparking key, the farmer in Georgia who woke at midnight to a crimson sky, the ship navigator whose compass would not settle, the astronomer in Surrey who ran to find a witness and came back to find the white light already fading. It was vivid, immediate, sensory, terrifying, and beautiful in equal measure. In the decades after, it became a scientific mystery, a data point, a reference event in the literature of geomagnetism and solar physics, something that specialists discussed in journals and conferences, while the rest of the world forgot it entirely. In the late 20th and early 21st centuries, as the power grid grew more complex and more critical, as the satellite constellation expanded, as the internet became the nervous system of the global economy, it became something else. A warning, a benchmark, a worst-case scenario in the risk assessments of engineers and emergency planners and insurance actuaries. Lloyd's of London published a report in 2013, written in collaboration with atmospheric and environmental research, that attempted to quantify the economic impact of a Carrington-scale event on the United States alone. Their estimate, between $600 billion and $2.6 trillion in total economic impact, with the high end of the range reflecting a scenario with prolonged, multi-year power outages in the most vulnerable regions. $2.6 trillion. In the United States, the insurance industry takes this seriously. The reinsurance giants, Munich Re, Swiss Re, Hanover Re, have space weather risk embedded in their catastrophe modeling. They are, in the most literal financial sense, betting money on their estimates of probability and impact. The scientific community takes it seriously. The 2008 National Academy of Sciences report, the work of Daniel Baker and his colleagues at the University of Colorado, the research programs at the British Antarctic Survey, the ongoing work of the NOAA Space Weather Prediction Center, all of it reflects a community of researchers who understand precisely what the sun is capable of and what modern civilization's exposure to that capability looks like. The question is whether the political systems, the legislatures, the regulatory bodies, the executive agencies, take it seriously enough to act before the event rather than after. The history of civilization is, in one reading, a history of the technologies we have built: the wheel, the ship, the printing press, the telegraph, the power grid, the internet. Each technology has expanded human capability, connected human communities, and created new kinds of vulnerability that the previous generation could not have imagined. The telegraph operators of 1859 had no framework for understanding what a geomagnetic storm was, but they had a framework for understanding that their technology could fail, and they improvised, brilliantly and resourcefully, when it did. They disconnected their batteries and found a way to send messages on auroral current. They evacuated burning stations and waited for the storm to pass. They rebuilt. The resilience of human beings in the face of technological failure is real. It is documented throughout history. It is not something to romanticize or to rely on as a substitute for preparation, but it is also not. The capacity to adapt, to improvise, to find new solutions under pressure is among the most consistently demonstrated qualities of our species. But there is a difference, a qualitative, fundamental difference, between the resilience needed to recover from a disrupted telegraph network in 1859 and the resilience needed to recover from a disrupted power grid in 2026. In 1859, the telegraph was an extraordinary convenience that had become, in some domains, an important operational dependency. But the underlying physical and social infrastructure of civilization, the farms, the roads, the ships, the mills, the stores of food and fuel, did not depend on the telegraph to function. When the lines went down, people could still eat, they could still travel. The basic metabolism of society continued. Today, the basic metabolism of society runs on electricity, not as a convenience, as a fundamental dependency. The water that comes out of the tap requires electrical pumping. The food in the grocery store requires electrical refrigeration throughout its supply chain. The medications in the pharmacy require electrical manufacturing, electrical refrigeration, electrical distribution logistics. The hospital requires electrical power for every life-sustaining intervention it performs. A prolonged power outage at the scale of a Carrington event is not a disruption to modern civilization. It is a threat to the physical survival of significant portions of the population that cannot manage without the infrastructure that electricity supports. This is not hyperbole. It is the straightforward consequence of how modern life is structured. And yet, and this is important, because this story should not end in pure despair, the same technology that has created this vulnerability has also given us tools that Carrington and his contemporaries never. We can see the sun in ways that Richard Carrington could not dream of. We can detect a CME leaving the solar surface and track it across the solar system. We have, at L1, monitoring systems that give us 15 minutes of warning before impact. Not enough to do everything, but enough to do something. We have the theoretical understanding to know what will happen and where the most critical vulnerabilities are. We have the engineering knowledge to address those vulnerabilities. We have the institutional frameworks, the space weather prediction centers, the grid reliability organizations, the emergency management agencies, within which coordinated preparation can happen. We are not in the position of the people of 1859 who had no warning, no framework, and no preparation. We are in a fundamentally different position. We are in the position of people who have read the warning and are deciding what to do about it. Let us close with Richard Carrington. He was 33 years old on the morning he watched white light erupt from the face of the sun and then, 60 seconds later, begin to fade. He was a careful man, a precise man, a man who believed in the importance of observation over speculation. He published what he had seen, drew no conclusions he could not support, and left the question open. In doing so, he gave us something extraordinary. He gave us the event horizon of our own vulnerability. A fixed point in the historical record that says, the sun did this. The sun can do this. And the next time it does, we will know what we are looking at. The science built on Carrington's foundation is one of the genuine intellectual achievements of the modern era. The space weather community, the solar physicists, the magnetospheric scientists, the ionospheric researchers, the electrical engineers, the emergency planners who have spent their careers understanding and trying to communicate this risk, deserves recognition for work that is, by its nature, mostly invisible. Preparation for disasters that have not yet occurred does not make headlines. It does not produce the kind of visible, dramatic results that attract attention and funding. But it matters. It may matter more than almost anything else we do. The Carrington Event of 1859 was the most powerful solar storm in the era of modern technology. It happened once. The physics guarantees it will happen again. The only question that actually matters from a practical standpoint is whether the next time it happens, we will have made the investments, built the resilience, and developed the operational capabilities to come through it with civilization intact. That is not a scientific question. The science is done. It is a question of choice. And choices, unlike solar cycles, unlike plasma physics, unlike the 11-year rhythm of the sun's magnetic heartbeat, are something we actually control. The sky over Surrey is quiet tonight. Somewhere, 93 million miles away, the sun is doing what it has always done: churning, convecting, building magnetic stress in complex sunspot groups that rotate slowly across its face, occasionally firing bursts of energy into the solar system. Sometimes big, sometimes small, sometimes, on a timescale of decades to centuries, extraordinary. Richard Carrington watched it happen once, on a September morning 166 years ago, and wrote down what he saw with the careful hand of a man who understood that observation, honestly reported, outlasts everything. His observation has outlasted It has outlasted every telegraph wire he ever saw strung across the English countryside. It has outlasted the electric telegraph company and Western Union's original form, and the entire Victorian era that produced him. It is still here, still waiting to be acted on. The star remembers. The question is whether we do. He saw with the careful hand of a man who understood that observation, honestly reported, outlasts everything. His observation has outlasted. It has outlasted every telegraph wire he ever saw strung across the English countryside. It has outlasted the electric telegraph company and Western Union's original form, and the entire Victorian era that produced him. It is still here, still waiting to be acted on. The star remembers. The question is whether we do.